Hi, everyone. This is the implementation session. Welcome. Please take a seat. We're going to start the talks very, very soon. My name is Alin Tomescu. I'll be your chair today. And yeah, I guess we can start right now. Our first speaker is Arash, and he's going to be talking about some very exciting work happening at Coinbase about their MPC library. Take it away, Arash.
Thank you, Alin, for the introduction. Yeah, I'm Arash, and I'm presenting Is it better now? All right. It's going to be hard to stay still. I'm presenting the CBMPC, Coinbase's open source MPC library, on behalf of the applied cryptography team at Coinbase, including myself, Yisho Chen, Yehuda Lindell, Gil Segev, Valery Yashater, and Samuel Ranelucci. So let's start with by introducing MPC. Secure Multi-Party Computation, or MPC, is a technology that enables multiple distrusting parties to perform a joint operation on their private inputs. So in the context of crypto key management, you can think of those private inputs as shares of a private signing key. And the computation that they want to perform is a digital signature, right? And the reason that MPC is a great fit for crypto key management is that it removes the single point of failure. So instead of an attacker compromising a single system and stealing the full private key, the attacker now needs to attack multiple different systems, potentially in different environments. One of them could be a cloud, a mobile, a laptop, different operating systems. So it makes it a lot harder for the attacker to go and compromise the system and gather all these pieces of information to construct a full key. Moreover, as you may know, an attacker doesn't necessarily need to steal the key to steal the funds. The attacker can just change the amount and the destination address and can drain a wallet. So that's why organizations typically put various policies, access control, verification on top of the actual signing scheme to make sure that they are signing the right thing. And the good thing about MPC is that it enables you to distribute those types of access control and those type of policy verification as well, and remove the single point of failure in that scenario as well. So, of course, MPC lends itself very well to the use case of custody and consumer wallet, which is what we have been using internally at Coinbase with great success. And we have decided to open source part of our production code because the community agrees with us that MPC is a good solution for this use case. And, but we do acknowledge that not every organization out there has the required expertise to implement a proper MPC protocol. And some of the open source libraries out there don't meet the bar when it comes to production grade security or code. And we believe that any breach to any organization is bad for the industry and by extension is bad for Coinbase. So by releasing our production code, we hope to increase the security posture of the whole community and gain better security for everyone. Moreover, our customer, by open sourcing our library, our customers can look at the code, look at our process, and we gain their trust by being transparent. We also get to benefit by open sourcing because there are more eyes will be looking at the code and with extra scrutiny to find any potential bug. This is an important thing that I will get back to and describe more about at the end of the presentation. All right, so I want to list out all the different features that we have provided because this is not just a threshold signing library. It has everything you need to build a proper MPC-based crypto system. We have organized our code into 3 main layers. The crypto layer, which is short for basic cryptographic operation. These include things like threshold encryption system based on TDH2, modular arithmetic, elliptic curve operation, Payet and Elgamal homomorphic operations, commitment, secret sharing, and the Lagrange interpolation, and of course, generating secure random numbers. On the second layer, we employ the first layer and build on top of that and offer zero-knowledge based functionality, including Fiat-Shamir and Fischlin transforms, various proofs on elliptic curves, including Diffie-Hellman and discrete log. We also have proofs on Payet keys and ciphers and Elgamal commitments and range proofs on them. At the third layer, we have our protocol layer, which include things like distributed coin tossing to generate a secure random number, committed group broadcast and also pairwise broadcast, integer commitment, OT and OT extension, and publicly verifiable encryption. We also have both two-party and multi-party DKG. We have an MPC-friendly way of deriving keys for HD wallets. And of course, we have both two-party and multi-party MPC signing for ECDSA and EDDSA. All right, so with that out of the way, you might be wondering, well, it's another library. Why should I care? And I'm going to spend the rest of this talk and try to convince you why you should give us a try. I'm going to base it by describing our guiding principles, which are our conservative security posture, our production-grade code, and our rigorous and transparent process of going from the research to code. So let's go over them one by one, starting with our security posture. So we have chosen simulation-based UC security proof as our main proof system because we believe that this is the gold standard when modeling real-world application in which the protocols can run in parallel, can interact with an arbitrary environment, and as a result, we prefer that over even game-based definitions. All our protocols are secure, are proven secure to be against malicious adversaries. For our proof model, we use random oracle, but we try to limit its usage to, for example, things like commitment or non-interactivity for Fiat-Shamir. We do not use a generic group model. As for the assumptions, depending on who you ask in the field, the definition of a standard assumption is different. We have chosen to rely on the 90s era as our standard assumption, things like decisional Diffie-Hellman and Payet, because these are the assumptions that have stood the test of time. The new assumptions do give us more efficiency, but they have not been working and playing in the field long enough for us to rely on them at this point. That's why we have chosen to rely only on the 90s era of assumption. And this notion of conservative approach to security over efficiency is something that is core to our design of the library, and that's why I'm going to spend a little bit more time on it and deep dive with an example. Consider the non-interactive zero-knowledge proof of knowledge. Typically, there are two ways of doing this, either using Fiat-Shamir transform or Fischlin transform. But in the UC security world, Fiat-Shamir gives us soundness and zero knowledge, but doesn't give us proof of knowledge. Because for the proof of knowledge, the extractor needs to rewind the prover to get two different transcripts based on the forking lemma. And this rewinding operation is not allowed in the UC security. So we get soundness, meaning that a dishonest prover cannot prove a wrong statement. We get zero knowledge, which essentially means that the proof doesn't leak anything about the secret, but we do not get proof of knowledge using Fiat-Shamir in the UC security world. Okay? However, with Fischlin, we can get all three of these properties and still be UC secure. And you might be wondering, all right, that's clear, let's use Fishling everywhere, all the time. But in practice, what's happening is that majority of the libraries out there, or maybe even all of them, default to Fiat Shamir. And this is because they think that they do default to Fiat Shamir because they think that Fishling is very, very too inefficient. And with this slide, I'm hoping to dispel this and put it in some perspective and show that it's actually not the case. And in the correct context, Fishling can be quite efficient as well. So to do that, I'm going to go a little bit into cryptography. So bear with me, please. I'm going to describe the zero-knowledge Diffie-Hellman and the zero-knowledge discrete lock, an example as two examples. So the Diffie-Hellman tuple we want to prove that a tuple G, H, A, and B, and these G, H, A, and B are elliptic curve points in an appropriate group. We want to prove that there exists a witness, a secret W, such that A is W.G and B is W.H. Okay, so that's what we want to prove. And we do want soundness, of course, and we don't want to reveal anything about W. And in the protocols that we are using in CBMPC, we do not need proof of knowledge, meaning that the prover doesn't need to prove that it actually knows W. The fact that this statement holds is enough. That's why in CBMPC, we use Fiat Shamir when we are implementing ZKDH and enjoy the efficiency that it brings with it. For the ZKDL, on the other hand, we want to prove that the tuple G and A is such that A is W.G. Note that in the for any point A in an elliptic curve point group has a W. So the soundness is trivial. It's not interesting. We don't care whether a W exists or not. We don't care whether this relation holds or not. The thing that we do care about is whether the prover knows W. And because we want proof of knowledge, we need to rely on Fishling, and we cannot use Fiat Shamir in the UC security world anymore. All right, so that's the end of the cryptography part. Let's see some numbers. If you go to our benchmark page, you will see that, for example, the ZKDH is 0.08 millisecond and, to generate a proof, and ZKDL is essentially 1 millisecond. And this is after heavy optimization and research that we have done, which essentially, in our experiment, Fishling is 15 times slower than Fiat Shamir. My point in this slide is that don't let this 15x scare you, because it's just 1 millisecond. And the question that we pose is that when protecting billions of dollars, and when the average transaction time is 10 seconds to 10 minutes given the blockchain of your choice, is it even worth it to try to save that millisecond? And in our use case, and in our opinion, no, it's not really worth it to save that millisecond. It's a lot better to rely on UC security and conservative assumptions. All right, so let's do a quick rundown of our parameters. For a statistical security parameter, we use 60-bit security. In some cases, for example, interactive cut and choose ZK proofs, we use 50K because we get significant efficiency gains. For computational security, we use 128-bit, which is in line for 256-bit of the elliptic curve point. We do not take any shortcuts for computation security. So for example, we do not rely on 80-bit security for ZK proofs. We also, wherever possible, try to use secure defaults. So whenever we are doing a homomorphic operation or PyE ciphertext, we do a re-randomization by default. Because if you do a homomorphic operation and you send the result to your counterparty, the resulting ciphertext could leak some secrets, something about the secret. That's why we do re-randomization by default. Of course, this is overridable. So for example, in our ECDSA 2PC implementation, we do a whole bunch of homomorphic operation one after the other, and then do a re-randomization once only at the end. We take the same approach when we are generating the session ID. So almost all our protocols generate a unique session ID internally, unless the user chooses to pass in an SID as input, in which case we trust that the user knows what they are doing and use that instead. We have taken a lot of care to write our code to be constant time. What this means is that whenever we are working on a secret, the operation, the time, should be independent of the secret value itself. I do caution that the constant time operations are CPU architecture dependent, and all of this is described, how we achieve constant time, and all of these nuances are described in our constant time documentation. I'm not going into detail here. I do encourage you to take a look later at the talk. Okay, so now let's talk a little bit about our production grade security. So our code is heavily tested, documented, and audited. All the features that I mentioned in the previous slide are written in C++. We have a very thin Go wrapper on top of it to make it easier to integrate into your systems. We are laser focused on the cryptocurrency use case. So as I mentioned before, we have all the tools you need for this use case. Not just the threshold signature, but you have publicly verifiable encryption, you have threshold encryption, and you have the OT and everything else that you need to do that. But we don't intend to be a general purpose MPC library. So for example, we will add things like garbled circuit if the use case exists for it in the future. I also want to point out that another part of production grade is our emphasis on creating a performant code. And I want to show that with an example. So consider the Lindell 17 the two-party ECDSA protocol. If you look at the numbers, we have gained significant efficiency by just writing a better code and being careful about what optimizations that we do. However, I do want to point out that the signing algorithm in the original paper was not a UC secure proof. It was a game-based proof, and it required a global abort. We do have it in the library, and that's the only exception that we have, but that is not our default signing. So our default signing is a UC secure signing proof, and the reason that we have provided both options is because of the efficiency gain. So if someone knows how to properly handle the global abort, which we have described in our documentation, they can do that. If not, by default, we use the UC secure one. We also have sorry, I want to now talk about our third pillar, which is our theoretical rigor. So our starting point is always an academic research, either an existing one of ePrint or something that we have done internally. Regardless of where we start, we always create a theoretical justification document. The purpose of this document is to describe and fill in the gaps that the original paper may have missing. For example, if the original paper doesn't have UC proof, we'll provide that. If the original paper talks about some parameters, we make them explicit and make sure that those parameters in combination with each other provide the level of security that we want. After that, we provide detailed specification. The goal with these specifications is to make sure that there is no ambiguity when it comes to implementing stuff. And among other things, these specifications include obvious, quote-unquote, obvious things that are typically missing from theoretical papers. For example, of course, a point should be on a curve and in a proper subgroup, and that's why most theoretical papers don't mention that. Or theoretical papers assume that an SID, a secure SID or unique SID exists, but don't talk about how to generate that. And these are the things that you can find in our specification. We have also provided our design principles, secure usage, and how to deal with constant time. I'm not going to go into details of it because I've already touched upon them. However, what I am going to do is just give you a taste of what our theoretical document look like. This is the table of content for our zero-knowledge justification document. As you can see, it's quite a long document. Includes the general treatment of sigma protocols, various proofs on elliptic curves, proofs on the PyEs, and other, for example, PDL or unknown order proofs. I do encourage you to take a look at it, but I won't go into detail right now. If you are interested in finding all these, we have in our README provide a table that you can start by, for example, a code and go to the theory or a spec, or you can start by a name and then find all of these. The goal here is to make everything traceable. So if there is any primitive or any protocol that you care about, you can easily find our paper, you can easily find our justification, our specification, and you can compare all the specification with the code and do the verification yourself and make sure that we didn't make any mistake. So this is essentially the last part of my presentation, and I'm going to show side by side how our specification and code compare. So on the left-hand side, you see the specification for EDDSA two-party signing, and on the right-hand side, you see the corresponding code. And what I want to point out here is how easy it is to read the code and match it to the spec. So for example, in the first line, we are saying that if job is P1, do this. So even if you don't know anything about the specification, you can guess that this is what party 1 is supposed to do. Or for example, in line 40, to multiply a scalar with a point, we have just overloaded the multiplication operator, so you can very easy to trace that. Or in line 43, when we have a network operation, we have made it clear in the body of the protocol itself where the network operation happened, instead of having, for example, it happening at a different function or different layer. So you can just put things side by side, go through them, and be convinced that things are behaving as they are supposed to. All right. So hopefully, by at this point, you are at least interested to giving us a try. And if you do, you can find us under Coinbase/CBMPC at GitHub. It is MIT licensed, so there's no restriction on how you can use the code. We do have a bug bounty program and security reporting, and you can find the details and security markdown file. I do want to point out that you have two main ways of doing this. You can either report through HackerOne and be eligible for a bounty, or if you don't want to be constrained by the restrictions of the bug bounty programs, you can just send us an email. We'll work out together, and you can then responsibly disclose on your own terms. And yeah, please try to break us and let us know. Thank you.
Thank you, Arash. Please ask Arash some questions. Before you do, I just want to thank you for the work and for raising the standard in our field. I think it's really nice what you said about a break to any one of us is a break to all of us. So
thank you.
Really appreciate it.
Hi. Nice talk. So I wanted to know, like, what communication channels do you assume between the parties? Is it like synchronous, asynchronous? I'm asking this because there's this annoying technicality with UC, a model that by default the channels are asynchronous. So you have to explicitly model synchronicity if you're assuming that. So like, how do you account for that in your proofs?
So it's different based on the protocol. So for example, for our signing protocols, we are assuming a synchronous operation. where did my slides go? I don't know. So so essentially, we are assuming synchronous communication. That synchronous communication channel, we do provide the interface for it. Okay, good. I can go back. So here in this, for example, P1 send to P2 job P1 send to P2. This is a synchronous operation, right? And to implement that, we have the interface provided. The actual implementation is outside of this library. We have provided a sample way of implementing it. For other things like threshold decryption or zero-knowledge proofs, these are by their nature asynchronous. So we have provided functions, and then you can call those functions in your environment however it makes sense.
And the UC, hello. And the UC proofs are also in the same channel that you assume for the implementation. Okay, thank you.
Thanks for the nice talk. Why C++ and not Rust?
So there are a couple of reasons. First is this readability that I am actually showing here is quite important to us, and achieving the same level of readability through Rust is not as easy. And the other winning argument for Rust is the memory management and the safety and all of that. We do have great developers internally that are very good at C++, and with their knowledge and also all the checks that we have around it, we are confident that we are not going to have that type of memory management problems. And instead, we can rely on this nice, verifiable, side-by-side verifiable that we get from C++.
Thank you.
That's funny because is it working? Oh, there we go. Right. Yeah, so it's funny because my first question was actually about so I haven't been following MPC for a while, but I'm going to start following again because it's super interesting, and I love these kind of real-world examples of use cases for it. And so my first question was about actually C++, and I was going to ask whether or not you chose it because of its ability to overload operators. Okay, and that's like a huge benefit, I guess, that you get from using okay, just for in terms of readability. And then the second, kind of along the same lines, is like who the actual audience is of the theoretical justification document that you produce. Is it like the internal research team, or is it scientists, or is it really developers that are reading through the theoretical justification?
So each of these documents have their own audience. So okay. The goal is that if you start from the theory, you can have small deltas to, for example, compare the paper with the theoretical justification, then compare the theoretical justification with the specification, then compare the specification with the code, instead of having a very abstract or high-level paper and then suddenly jump to code, okay? Now, who is performing that delta verification is depend on the expertise. So an academics may be only interested in that first part, but an academic with some programming or specification flavor can look at the second delta, and the developer can look at the third delta from the specification and the code. So choose your own journey. We are looking for everyone to look at any and all of these things that we have open source, and let us know if you find any problem.
Very cool. So you built like kind of the ladder of you have, okay, the goal is to reduce the amount of verification that you have to do at each step, I guess.
Yes.
Okay, thank you.
Yes.
Hi, thanks for building this. This is super helpful to us, especially the cryptocurrency applications. I'm curious, how long did it take and how many people did it take to actually develop it? Because this is like a huge project. If you can share some insight on the kind of economics of building this.
Yeah, I mean, it's hard to give you an exact number because it happened over many years and different people were working on it, and of course, people were working on part of it and working on other projects, so developers were not always working on this, so it's hard to give you an exact number. But the people in this list are our cryptographers and our developers, so a mix of these people over a couple of years.
Thank you.
All right. Sorry, we're running out of time, but please follow up with Arash after.
Awesome.
Let's thank the speaker one more time, and thank you. Our next speaker is Deepak Maram. He's a cryptography research scientist at Miston Labs, and he's going to be talking today about some new work on key management and authentication.
All right. Hi, everyone. This is Deepak. I'm a research scientist at Mistral Labs. Today, I'm going to talk about our new work on authentication. This is joint work with Itai Ayal from Technion and Mahimna from Cornell Tech. So the focus of our work is how to improve security of authentication mechanisms. Now, authentication mechanisms are used everywhere, both in Web 2 and Web 3. And a really, let's say, common paradigm we see across the board is to try and split the secret into shares so that even if one of the shares is lost, your scheme is still secure. And in fact, this is sort of the focus of the prior talk. And we see something like multi-factor authentication used heavily in Web 2, and even if you go to Web 3 and ask yourself, like if you search what is a safe way to store my key, you will find several blogs and articles saying use multi-sig wallets or threshold signatures as ways to kind of improve the security of your key management scheme. But the reality is that hacks keep happening. And in fact, in several of these hacks, they explicitly use exactly the same sort of techniques that we recommend them to use, namely multi-sig schemes or threshold signatures. So the July 2024 hack on the slide here, where about $200 million were hacked, was from a Gnosis Safe multi-sig wallet, which was a 4 of 6. And you'll see similar examples all across the board. So this kind of state of things leads us to ask, well, is this sort of the best we can do, or is there something better we can do to improve the security of these systems? The key insight of our work, which we use heavily, is this pattern that I'm going to call interaction pattern. And this pattern is so general that I'm sure many of you may even have seen the use of it in your own lives, either in the physical world or the digital world. Let me just explain what this pattern is through an example by taking the example of a bank called HDFC Bank, which employs this in sort of the Web 2 world. So if you want to add a new beneficiary in the bank allows you to do so by submitting both a password and an OTP received on email or mobile. But the beneficiary addition does not happen instantaneously. It only happens after a delay period, in this case of, let's say, 30 minutes. This period basically serves as a window of opportunity for the user to kind of recover their account if something bad happens. So the user can, within this period, go back and, for example, cancel the addition. And essentially, the reason this is useful is that even if your account got hacked for some reason, and an attacker is trying to steal all your money, there is this window of 30 minutes where the user can, if they were sufficiently alerted and if they could kind of get an access to a device to cancel this operation, they can still secure their account. So this is what we call interaction pattern. As you can imagine, this kind of relies on some sort of a synchrony assumption, because if the user is unable to respond to the alert notification that the bank has sent within that period of 30 minutes, then sort of this scheme doesn't make any sense. But if we can make certain synchrony assumptions, it appears that we can sort of get more security out of our system. And in fact, this pattern is so widely used that there's many crypto wallets that already use it. Argent crypto wallet is one example of a wallet that uses it. In fact, it is so generic that even the IRS uses it in sort of the pre-digital era, where so the IRS actually sends you a notice alerting you about like potential identity thefts and gives you like a window for you to go and take some action to revert any malicious action that may have happened in case of identity theft. So this pattern is very generic, and essentially what we do in our work is to introduce a model for us to kind of frame and talk about authentication mechanisms in a level on sort of a level playing field, and this model is sort of rich enough to model or capture the interactive mechanisms or the pattern that I just mentioned. Then I'll go on and introduce several new mechanisms, and these mechanisms will leverage the interaction pattern that I just mentioned. What's interesting about them is that we prove that they are maximally secure, meaning that these mechanisms meaning that no other mechanism is more secure than these mechanisms, which is sort of a very strong result that we have. And lastly, we take all our insights and use them to analyze a few real-world mechanisms, some of them interactive, many of them non-interactive, and see how our mechanisms fare against what is sort of widely used in practice. Yeah, with that, let's jump into how our model works, and then I'll take you through the rest of the talk. So our model is quite broad and generic, purposefully. So we basically have two entities in our system, a user and an adversary. So the user is the one who sort of owns the money or the identity or whatever it is we're trying to secure. And an adversary is essentially anyone who's trying to break into and act as the user. Credentials are also modeled very generically. We can capture any credential you can think of, from password to biometric. We just assume that there are n credentials in the system, and there is a mechanism which kind of stores maybe your money or your identity, and it uses some combination of these n credentials to safeguard your funds or your identities. We model credential states in the following manner. Basically, we say that each credential can be in one of 4 states, depending on which of these two parties has access to the credential. If the credential is safe, then only the user knows the credential. If it is lost, then sort of no party has access to it. If it is leaked, then both parties, meaning the user and the attacker, has access to the credential. And if it is stolen, only the attacker has access to the credential. In this particular work, we are going to assume that the knowledge of the state of a credential is public, meaning that the user knows and everyone kind of knows that the credential is stolen. Of course, in practice, the situation can be messy in that sometimes maybe the attacker knows that something is stolen before the user. Sometimes maybe the user knows that their credential is lost before the attacker knows. Just to keep things simple for this work, we kind of assume that the knowledge of the state of a credential is the same for both the user and the attacker. And then we can start looking at concrete mechanisms and see how they perform under different scenarios. So let's say we have the following scenario where we have 3 credentials, blue, silver, and green. The user has all 3 credentials, but the green credential is also leaked, so the attacker also has access to it. So now in this particular scenario, we say that the 2 out of 3 mechanism succeeds because only the user can authenticate. Whereas in this exact scenario, we say that the 1 out of 3 mechanism fails because the attacker can authenticate. So the determining factor here is whether the user alone can authenticate or not. So especially in the 1 out of 3 scenario, you can notice that both the user and the attacker can authenticate, but we kind of conservatively assume that the attacker will be able to authenticate ahead of the user and kind of mark it as a failure. So given this, we can already start mapping out how a mechanism performs in different scenarios. So for example, let's take the 1 out of 2 mechanism or the OR mechanism. So we have this 4x4 matrix of which maps out all the possible credential states. So essentially, at any given point in time, we are in one of these 16 table cells. Initially, maybe both the credentials are safe, but as time goes by, maybe one of these credentials gets leaked or lost or stolen, and we kind of move across this matrix of credential states. And we can essentially, like I mentioned in my previous slide, we are going to mark a cell as a tick mark if the mechanism succeeds in that scenario, and mark it as into if it fails. So you can sort of easily notice here that a 1 out of 2 mechanism succeeds in just those 3 scenarios that I kind of marked in the table. Basically, it succeeds if both the credentials are safe, or it succeeds even if one of the credentials is lost, because that's sort of how the OR mechanism works, where submitting any one credential out of the 2 is enough. Now we can sort of do this for different types of mechanisms. So I just showed the profile for the OR mechanism. You can look at the profile for the AND mechanism. So the AND mechanism's profile looks slightly different. Whereas the OR mechanism succeeded if one of the credentials was lost, the AND mechanism fails. Instead, the AND mechanism succeeds in scenarios where one of the credentials is leaked, because again, recall that leaked means that both the user and the attacker have access to the credential. So therefore, even if one of your credentials is leaked, the mechanism still succeeds. Just for simplicity, we can also look at the really simple one-key mechanism. So this is a mechanism where you're only using one of the two keys. And so if that key is safe, you're good. But if that key is unsafe, you're not good. And here's where it starts to get interesting, because we can use these profiles to compare different mechanisms. Essentially, we can say that a mechanism is either better or worse or equivalent or incomparable to another mechanism just by looking at their profiles. We say that a mechanism is better than another if its profile is sort of a superset of another mechanism. So a profile is basically all the scenarios in which it succeeds. So you can see that the blue mechanism here has 3 scenarios in its profile, whereas the yellow mechanism has only 1 scenario in its profile. And in fact, the profile of the yellow mechanism is a strict subset of the blue one. And so we say that the blue mechanism is better. And similarly, worse is sort of equivalently defined. And we say 2 mechanisms are equivalent if they have the same profile exactly, or even after some permutation of the credentials, and as you would sort of naturally define it. And finally, we say that 2 mechanisms are incomparable if none of the 3 prior relations hold between them. So one example would be these 2 mechanisms here, where so the blue one is incomparable to the yellow one because there's no clear subset relation between the 2 profiles of these mechanisms. Extending that thought further, you can place all the mechanisms that exist in the world on a single plane and draw an arrow if there is a better-worse relation between them. And you would get an image like this, which essentially maps out all the mechanisms that there are, and you get this, let's say, neat structure between the full set of mechanisms. And as I said, the arrow kind of denotes the better-worse relation. So in this particular case, the black mechanism is worse than the green mechanism. That's why the arrow is kind of in that direction. Whereas these top 2 mechanisms are incomparable with each other. That's why there's no arrows between them. Same for these bottom ones. And what's interesting about this graph is these mechanisms that sit at the very top. So these are mechanisms that we refer to as maximally secure mechanisms because by definition, there's no other mechanism that is sitting on top of these. So these are mechanisms such that there's no other mechanism that is more secure than them. And these, as you would imagine, are sort of interesting for us, even from a practical sense, because these offer sort of the best security that we can hope to achieve. And lastly, we use the term complete maximal set to refer to this full set of top level mechanisms. So this complete maximal set is basically the set of all maximally secure mechanisms such that you pick any other mechanism in the world, it is worse than one of the mechanisms in this set. And so if you are a practitioner looking to implement a mechanism for your purpose, you would naturally look at the complete maximal set and ask yourselves, which of these mechanisms should I use in my particular case, basically. So with that said, I will move to the sort of the second part of the talk, where I will introduce some new mechanisms that we have that are actually maximally secure. So our mechanisms are actually very simple to understand. I will go through them in this slide, and they all follow a very simple format that I will explain now. So basically, the mechanism works as follows. Any party can sort of trigger the mechanism by submitting a credential, and as soon as the mechanism is triggered, there is a timer that starts. And also the mechanism is going to send alert notifications to all parties, especially the user. So in this case, if that attacker has tried to, let's say, initiate an action, the user we are assuming that there is a synchronous channel between the mechanism and the user, which allows the user to know about the action that happened on chain. And then maybe the user submits a few more credentials, maybe the attacker submits a few more credentials. So basically, once the timer runs out, the mechanism just looks at the set of credentials submitted by different parties, and it goes and it inputs these sets of credentials into a deterministic function, which outputs who the winner was. So for example, maybe the function f says that the user is the winner, and then the mechanism says the user wins. So this is sort of a very simple template of how all our maximal mechanisms work. The first class of maximal mechanisms that I'll introduce are called priority mechanisms. And as the name suggests, the way they work is that the mechanism designer needs to a priori define a priority between all the credentials they have in their system. And this priority is going to be leveraged when we are going to sort of judge the things at the end. So the rule or the function f from my previous slide that is going to be used is basically that the highest priority credential that is sort of not submitted by the other player wins. Essentially, if both parties submit a bunch of credentials, we're going to remove all the credentials submitted by both parties and then look at the unique credentials and see which one is sort of the highest priority one and mark them as the winner. Just to go through an example, so let's say that this is the priority, and maybe the user submits the purple credential, whereas the attacker submits the rest 2 credentials. In this case, the user is going to be marked as a winner because the highest priority credential that is not submitted by the other player is the purple one, which the user holds. Whereas if the user submits these 2 credentials and the attacker submits just the silver credential, again, the user is marked as a winner because the silver credential gets canceled out and the gold credential leads to a win for the user. And it turns out that this simple priority mechanism has the following profile. Basically, in all the scenarios where the highest priority credential is safe, the user is going to win because it's the highest priority credential, and irrespective of what happens to the other credential, the user is going to submit that and lead the mechanism to an action that they want. If we look at the scenarios on the rightmost column, especially the scenarios where, let's say, the highest priority credential purple is lost or it is leaked, even then it's fine because in both lost and leaked, it's either that both parties don't have access to the high priority purple credential or both parties do have access to it, and therefore it kind of doesn't matter. And as long as the silver credential is safe, we're good. That sort of leads us to this profile where we have basically 6 scenarios in the profile of the priority mechanism. And you can sort of visually notice that the priority mechanism has a better profile in the sense where I use the term better in the sense that it is more secure than the 3 simple mechanisms that we know of, like the OR mechanism, the AND mechanism, and the one key mechanism. So this priority mechanism turns out to be more secure than these 3 simple sort of non-interactive mechanisms. A second class of mechanisms are majority mechanisms. So these are, again, very similar in the way they work, except that the winning rule here is that whoever submits the most credentials wins. This may be more intuitive in certain contexts where you just want to say that whoever submits the most credentials wins. There is some nuance in the case of a tie where like both parties submit equal number of credentials, but a different set of credentials. Like maybe there's 3 credentials and user submits credentials 1, 2, and the attacker submits credentials 2, 3. Now the mechanism needs a way to decide who wins. So you would have to define certain tie-breaking rules for the mechanism to kind of determine who wins. But all in all, majority mechanisms kind of also get the same profile. And in fact, we have a result that shows that no mechanism can succeed in more than this number of scenarios, which is what allows us to prove that the 2-credential priority mechanism is maximally secure. Now the intuition for the result is maybe somewhat easy to see. I hope it is easy to maybe observe that, especially in the 3x3 matrix where both the credentials are not safe, there's no way that we're going to ever hope to win. And then we have a result showing that that a win in certain scenario leads to a loss in some other scenarios. And that allows us to kind of come up with this number of 4 power n minus 2 to the n by 2, which in the case of n equals to 2 leads to 6. And that is the same number of, that is the size of the profile of the 2-credential priority mechanism we saw before. Lastly, all our mechanisms are fairly easy to implement on many chains, especially if your chain has smart contracts. It's fairly straightforward to implement. And in fact, the priority mechanism can even be implemented on Bitcoin using time locks, and this is sort of a company that is trying to do that if you're interested to check out. So with that, I'll kind of go into our real-world evaluation of all these mechanisms against some existing mechanisms. So Argent and HDFC are two case studies that we took up. Basically, these are mechanisms that are already interactive, that are already deployed out there in practice, used by millions of people. But it turns out that these mechanisms aren't, let's say, as secure as they can be. So we propose, so we find some more improvements in their mechanisms, as I'll talk about next briefly. So as far as the 2-credential mechanisms is concerned, this is how the map of all the mechanisms we've analyzed looks like. So the 1 out of 1, so I've already talked about the OR mechanism, which is the 1 of 2 mechanism, the AND mechanism, the 2 out of 2 mechanism, and the single key mechanism before. So we find that Argent's mechanism kind of sits somewhere in between our priority mechanism and these simple non-interactive mechanisms. I won't go into the details of our analysis in the interest of time, because the mechanisms of Argent are like fairly complicated. But feel free to check out the paper if you're interested. As far as the 2-credential mechanisms are concerned, we have a result showing that the complete maximal set of 2 credentials is actually of size 1. It just has the priority mechanism. This basically means that if you ever want to deploy a 2-credential mechanism, priority mechanism is sort of your go-to, and that's it. The situation for 3 credentials is way more complicated or interesting, depending on how you want to look at it. So as I mentioned before, we have priority and majority mechanisms. So what happens, especially in the case of 2-credential mechanisms, is that the priority and majority turn out to be the same. That's why we just have the 1 mechanism there. Whereas for the 3-credential mechanisms, they turn out to be different mechanisms. So that's why we have more mechanisms at the top. We find that the 3-credential complete maximal set is much richer with like a size 14. It's just composed of priority and majority mechanisms with all sorts of different tie breaks. But I would imagine that the simple priority and majority mechanisms are sort of the most practically relevant and interesting ones for people to look at. And like before, we find that both in the case of Argent and HDFC, their mechanisms are not as secure as they can be. In fact, for both Argent and HDFC, they're both worse than the priority mechanism. Whereas the 2 out of 3 mechanism, which is, let's say, a really popular non-interactive mechanism that people use all across the board, is worse than the majority mechanism. So our mechanisms offer much better security than many that people kind of commonly use today. There's a lot of future research directions that are interesting here. In particular, we picked a very specific model that is kind of easy, that allows us to make easy analysis. And there's many variations here that could be interesting both for theory and practice. As I've mentioned at the start, we assume complete knowledge of the scenario, meaning that both the user and the attacker know the exact state of each credential we have. It may or may not be the case depending on the type of attack you have in practice. So it could be interesting to consider models where the knowledge of the scenario is hidden. Maybe the attacker knows more, or maybe the user knows more. There's many variations that are potentially interesting here to consider. Communication models, in terms of communication models, we assume synchrony. There is another work in asynchrony that I've kind of pointed to there. Things are way more dry in asynchrony. You can't do much better than the simple sort of non-interactive stuff. But it is interesting to maybe consider hybrid models that have both synchronous and asynchronous aspects. And lastly, there is also some prior work in using incentives to kind of improve the security of mechanisms further. Vaults is one that some here may know of, but it is definitely interesting to consider incentives to further improve the security of mechanisms than whatever we have shown here. With that, I'll conclude my talk. I have so our work presents a generic model to evaluate any mechanism, and if any of you are interested or want to model your own mechanisms in our framework, feel free to do so, and I'm happy to chat about that. I would say that primarily our work highlights the importance of interaction or using delays in your mechanism. As I sort of quote there, if your mechanism is worth like $100 million, I'm sure you can add like a small delay in there if it's going to help improve the security of it. And our work proposes new mechanisms that are maximally secure and kind of easy to use and deploy. Yeah, with that, I'll conclude my talk, and thank you.
Any questions for Deepak?
Thank you for the nice talk. I have two questions. First, all this analysis regards public keys and private keys, not passwords and stuff, right? Or does
Not what, sorry?
Passwords, one-time passwords.
So this could also be modeled, so passwords could also be modeled here, because our model isn't really talking about exactly what type of credentials you use. So I think this could very easily also be used in a Web2 setting where you're trying to think about how to improve your security, and credentials are maybe passwords or biometrics or any other things really. So nothing here is assuming that you're using a specific type of authentication mechanism.
Right, but some types of credentials are much more easily leaked, like passwords
Sure.
as opposed to...
That's right.
Yeah.
Yeah. So that's there, but I think that is sort of orthogonal to what we're doing, in the sense that you can model any credential in our system, and maybe each credential has a different characteristic, in the sense that some are more prone to be lost, some are more prone to be leaked. And then there is sort of a question of how do you combine different credentials given those characteristics, which could be interesting. We haven't looked at or tried to answer that type of a question, but
The other question I wonder about is what happens when with cold storage versus hot storage.
right. Yeah, so I think again, cold storage and hot storage are sort of orthogonal to our work, in that you can model any credential with our work. Maybe the interesting question to ask is, like, if you think that, let's say, cold storage has certain probability characteristics and hot storage has a different probability characteristic, which mechanism should we use given those probability characteristics? So that sort of questions are fairly easy to answer if you have a specific probability characteristic. In particular, the way you would do that is just look at the complete maximal set and see, for your given probability characteristics of credentials, which one is best. And one of these, so basically these mechanisms in the complete maximal set just differ in that aspect, essentially, in that given your probability characteristics, one of them may be better than another. But since this set is sort of the best you can do, you don't need to look outside this set.
If you have 28 good scenarios, but they can fail with a high probability versus another setting which has fewer ticks, but which are more reliable, maybe something that is outside the maximal set could end up better.
No, so the definition of a complete maximal set itself is that it comprises the full set of mechanisms at the top. Basically, whatever your mechanism is at the bottom, there is a mechanism in the maximal set that is more secure than that. So given your probability characteristics, some mechanisms in the complete maximal set may be bad, but there will be, so whatever mechanism you come up with me, it is either already in the maximal set, or there is a mechanism in the maximal set, complete maximal set, that is better than that, basically. Yeah.
I think we're running out of time. Maybe you can follow up with Deepak after. Thank you. Please, let's thank Deepak one more time. Very nice work. Our next speaker is Rex Fernando. He's a cryptography research scientist at Aptos Labs, and he's going to be telling us about batched threshold encryption and its application to MEV protection.
Thanks, Ellen, for the intro. Yeah, so my name is Rex. Can everyone hear me? That's good. Okay. Yeah, so I'm Rex. I'm going to be talking about some work that I did last year jointly with my collaborators Amit Agarwal and Benny Pincus. Okay. Okay, I think we're back online. Yeah, so this work is on a new type of encryption scheme, and specifically, we define and study a variant of identity-based encryption, or IBE. So to introduce IBE and to introduce our scheme, let's start with standard public key encryption. So with public key encryption, let's say you want to start to receive encrypted messages. The first thing you have to do is to generate what's called a key pair, and this key pair has a public key, which you have to post somewhere public that's easily accessible, and it also has a secret key which you cannot post publicly, you have to keep secret. And so if someone wants to encrypt a message for you, they have to first look up your public key wherever you posted it, and then that public key allows them to derive a ciphertext which is only decryptable by you, assuming only you have the secret key. So the key thing here, the kind of secret sauce that makes this work, is this key pair. Specifically, this public key almost always has some sort of, algebraic structure that depends on the secret key. So IBE, or identity-based encryption, is similar but different. And the way that it's different is that instead of having to encrypt with respect to some structured public key, it allows you to instead encrypt with respect. Okay, is it better now? Okay. Yeah, so the way IBE is different is instead of encrypting with respect to structured public keys, you can now encrypt with respect to an arbitrary string as your public key. And this string is called an ID in the context of IBE. And the reason why this is meaningful and useful is because in IBE, we also assume that there's some sort of key issuing authority that has a master secret key. And this master secret key allows you to derive a secret key corresponding to any of these strings, any of these IDs. And this secret key can then decrypt ciphertext under IDs that match. Okay, so why is this useful or interesting? Well, first of all, it makes key management easier. Second of all, you can actually do things with IBE that are impossible with public key encryption. For instance, you can compute a ciphertext for an ID before the corresponding secret key to that ID even exists. And because of this flexibility, you can start to handle even crazier scenarios. You can start to think of IDs as corresponding not to people, but maybe to events. So you can imagine a key issuing authority that publishes a secret key every hour on the hour, where the identity is just the timestamp for that hour. And then suddenly you have encryption to the future. You can just encrypt to a future timestamp, and then it'll only be decryptable on that hour. So that's IBE. It's a really interesting and useful primitive, and this is what we study in this work. And specifically, we're going to study a particular type of efficiency problem related to IBE. So let's say that we have a large set of IDs. Let's say that there are n different IDs. And what we want is we want to generate a single secret key that can decrypt ciphertext under any of these given IDs. So how do we do that? So if we have just a standard IBE scheme, then the only thing that we can do is we go one by one with each of these IDs, and we use the master secret key to derive an individual secret key for each of these IDs, and then we just concatenate them. And this is sort of our quote-unquote secret key for this set. So why is this bad? Well, first of all, this quote-unquote secret key is order of n sized. So it can be very large depending on the size of the set of IDs. And also it's inefficient to compute. Computing the secret key is also order n time. So why is this efficiency problem interesting? You know, why should you care? Well, it turns out that this specific efficiency problem becomes an important scaling issue when you try to implement mempool privacy. And of course, mempool privacy is an important tool for combating MEV. And it also turns out that this becomes an important scaling issue for other sort of interesting on-chain functionalities. Basically, whenever you want to implement threshold decryption on-chain, you could potentially run into this issue. So like I said, we're going to try to solve this issue with our work. And the way that we're going to do this is by introducing what we call batched identity-based encryption. So with batched identity-based encryption, we're going to make the following changes. So first, we're going to have, so given a set of NIDs, we're going to have a procedure that allows us to compute a succinct digest that sort of commits to this set of IDs. And notably, this digest procedure is going to be public. It's publicly computable. It doesn't depend on the secret key at all, the master secret key. With this change, we're also going to change our key derivation procedure. So instead of taking an ID directly, as in with normal IBE, this key derivation procedure is going to take this digest, and it's going to generate a secret key corresponding to this digest. And the idea is that the secret key should be able to decrypt any ciphertext with any ID that was committed to in the digest. And crucially, we're going to require that this secret key and also the digest are going to be constant sized. So the size doesn't depend on the number of IDs. And also we're going to require that the key derivation procedure is also constant time. So again, it doesn't depend on n. And so it should be clear that if we can instantiate a scheme like this, then it solves because of these efficiency requirements, this scheme should solve the problem that I posed on the previous slide. Okay, so this is like essentially the goal of our work is to instantiate such a key scheme. But before I go on, I just wanted to give sort of a slight caveat to this, and that is for technical reasons, we actually weren't able to exactly instantiate what's on the slide right now, and instead we had to make some slight sort of syntactic changes, and I'm going to describe these changes now. So first of all, we're going to change the ciphertext slightly. So the ciphertext is going to it's going to be defined not just with respect to an ID, but also with respect to some other identifier, which we'll call the batch identifier. And in addition to this, the secret key derivation procedure will also take in such a batch identifier. The secret key will be with respect to the batch identifier and digest. And the idea is that this secret key should be able to decrypt any ciphertext whose ID is committed to in this digest and whose batch identifier matches up. So this sort of syntactical modification might look a little sort of arbitrary and artificial to you. So I'll just say that, and again, we had to make this modification for technical reasons. I'll try to explain these reasons in a little bit more detail later. And I also want to say that, for the applications that we were considering, we're still able to achieve all of those applications even given this small syntactic change. And so you can either believe me with that or you can read the paper where there are more details on this. Okay, so with that, I'll present our results. So we give this new definition of a batched identity-based encryption scheme, or IBE, and we also give a construction using pairing-based groups. And specifically, our construction can use any type 3 pairing. And in terms of security, we give a security proof in the generic group model. And in addition to this first scheme, we also give another scheme that's a batched public key encryption scheme, so non-IBE. And this scheme satisfies a stronger form of CCA security, which turns out to be crucial for achieving mempool privacy. And finally, we have an implementation. The implementation is in Rust, and it's using the ArcWorks crypto library. Okay, so for the rest of the talk, I'm first going to try to go over our construction and give you sort of a high-level idea of the pieces in our construction and how they fit together. And then in the remaining time, I have several applications I'd love to talk about, but in the interest of time, I'm going to focus on mempool privacy. Okay, so just fair warning, this is the technical part of the talk. There's going to be some cryptography. So like I said before, we're going to work in a pairing-based setting. So there's going to be three groups with a pairing between them. And also, I just wanted to note that in this talk, I'm going to use additive notation for the group operation. Okay, so now for the construction. So let's start with the easy part. And the easy part turns out to be this digest procedure. So recall that the goal is to take a set of IDs and come up with a constant size digest. And why is this easy? It's because it's already solved many times in the literature. So let's just assume that the IDs are field elements, and then I'll explain the particular scheme that we use from the literature for solving this problem. So the first step that we're going to do is we're going to take these IDs and encode them as some polynomial f. Specifically, for our construction, we're going to use the vanishing polynomial over the ID set. And step two, we're just going to use the KZG polynomial commitment scheme to commit to this polynomial f. So a quick review of KZG. It has a setup. The setup consists of basically Feldman commitments to like these powers of a secret tau. And committing to a polynomial involves using this setup to basically derive a Feldman commitment to an evaluation of f on this secret tau. And notably, this commitment, this evaluation, is constant size. So we can use this as our digest. And then another property about KZG that we're definitely going to use in our construction, but which I'm going to try to sweep under the rug as much as possible in this talk, is that KZG also allows you to compute succinct proofs of evaluations of the polynomial with respect to the commitment. And for us, this means we can compute succinct proofs of set membership. Okay, so that was the easy part. Now to the hard part, which is how, we have these digests now. So given a digest, how do we compute a corresponding secret key for the digest? And also, how do we come up with a ciphertext that sort of unlocks given these secret keys? And to do this, our construction is going to take heavy inspiration from this classical Bonnet-Franklin IBE scheme. And so I'm going to explain the Bonnet-Franklin IBE scheme at a high level now. So Bonnet-Franklin has this very beautiful strategy where it sets, recall it with IBE, there's a master secret key. So the Bonnet-Franklin IBE scheme sets its master secret key to be the signing key of a signature scheme. And specifically, it sets it to be the signing key of a BLS signature scheme. And then on top of that, so a secret key in Bonnet-Franklin, a secret key for a given ID is nothing other than a BLS signature over that ID with respect to the master secret key. And here, you can think of a signature over an ID as sort of meaning an authorization for decryptions with that ID. And then finally, Bonnet-Franklin has this nice way of generating a ciphertext that sort of respects those authorizations. Essentially, it unlocks given a signature over the ID. And the way it does this, I'm not going to go into details, but essentially it builds a ciphertext based on the BLS signature verification equation. So BLS has this nice pairing-based signature verification where, and so Bonnet-Franklin basically builds a ciphertext such that if you can solve this equation, if you have a solution, then you can decrypt. So essentially, we're going to try to generalize this approach to our setting. So for our first step, recall that instead of generating secret keys with respect to individual IDs, we want to generate secret keys with respect to digests that commit to whole sets of IDs. So we're going to do that just by, instead of signing IDs, we're just going to sign digests. And so now you can think of this, this decryption key, this signature over the digest, as authorizing decryptions with any ID committed to by that digest. And then finally, our second step is that we're going to try to generalize the Bonnet-Franklin ciphertext somehow. So remember that with Bonnet-Franklin, the way that it works is the ciphertext is decryptable if you can basically solve this constraint. And the constraint is you have a signature over this ID. So we're basically going to do the same thing, but we're going to have a slightly more complicated set of constraints. So the first constraint is that to decrypt a ciphertext, you need to provide an ID and a proof that the ID, provide a digest and a proof that the ID from the ciphertext is committed to in the digest. And second, you need to provide a signature over the digest with the master secret key. So to do this, let's think a little bit more about the Bonnet-Franklin ciphertext. So like I said before, the Bonnet-Franklin ciphertext is built with respect to this verification equation, this BLS verification equation. But it turns out that nothing about Bonnet-Franklin, nothing about this BLS verification equation is actually that special. And in fact, you can actually build sort of a Bonnet-Franklin-like ciphertext for any sort of pairing-based equation that has the same form. So you can build a ciphertext that sort of fixes this A and B, these coefficients A and B, and then if you can solve this equation, you can decrypt. And it turns out that you can actually generalize this even farther. So you can actually generate these sort of generalized Bonnet-Franklin ciphertexts that basically are generated with respect to an entire system of these sort of linear-like pairing-based equations, where the ciphertext fixes these coefficients, it fixes the A's and the B's, and then you can decrypt this ciphertext if you can basically fill in all the blanks and solve the equation. So here, like your solution to the equation is essentially your decryption key. Okay, so essentially we're going to try to use this framework to instantiate our ciphertext. So what does that mean? That means that essentially all we have to do in order to finish is we just have to write these constraints as a system of equations, that that follows that structure, that from this pairing-based equation structure. And once we do that, we're just finished, because then we have a ciphertext, we have a decryption key, and we have the digest. And it turns out that instantiating this part way is actually quite easy. So the first part of, the first constraint that we want to use, that's very easily writable as a pairing-based equation. So this first constraint is this proof that an ID was committed to in a particular digest. But it turns out that the second constraint, the signature-based constraint, actually is harder. It seems like kind of a roadblock. So this might be kind of surprising to you, because you might be thinking, okay, so wait, so original Bonnet-Franklin involved basically verifying a signature as a linear equation, so why is this any harder? But there's a crucial difference here. So before, with original Bonnet-Franklin, remember that the ciphertext fixes an ID, and this ID is basically the message for the signature. And what that means specifically is, if you were paying attention to the specifics of the BLS verification equation, you actually have to hash the message that you're signing and that you're verifying. And like with Bonnet-Franklin, you can actually embed the result of this hash as a coefficient. So you can basically pre-compute the hash. But with us, things are different, because now we're trying to verify a signature over this digest. And this digest is actually not fixed at ciphertext creation time. So what this means is that somehow it seems like you might have to sort of, to instantiate this, you might have to actually sort of embed the hash computation, or at least a verification of a hash computation, as part of the system of linear equations. And that seems like a hard problem, because hashes are quite nonlinear. So basically, to finish instantiating our scheme, we're basically not going to solve this problem. We're just going to go around it. And the way we're going to go around it is by changing the BLS signature scheme. So if you know anything about BLS, you know that the signing algorithm is actually very simple. All you have to do in order to sign a message is you just have to take the message, in this case D, you hash it into the group, and then you multiply it, you do a scalar multiplication by the master secret key, and that's it. And recall the only part of this that's problematic is the hashing of the message. So to fix this, we're just not going to hash the message. Instead of hashing the message, we're first going to offset the message by the hash of some other value. And then once we have this offset message, this message that's offset by the hash, then we're going to, again, do a scalar multiplication, just as in BLS. And the crucial thing here is that we're going to have that this hashed value is going to be fixed at creation time. And it turns out that this sort of simple modification of BLS is secure as long as you don't reuse these values B. Like as long as you don't give out two different signatures with the same hashed B value. Okay, so with this modified BLS, that's basically the final piece of the puzzle, and we're able to write out all of the constraints as like one big linear equation system, and that finishes the ciphertext instantiation. So now we have the ciphertext instantiation, we have secret key generation, secret key derivation, which is just signing, and then we have the digest procedure, which is just KZG. So that means so that means we have all the pieces, and this is basically an outline of how the construction works. So there are a few details that I didn't discuss. Maybe you noticed. One is how do you thresholdize such a scheme? But it turns out that thresholdizing is actually very easy because basically you thresholdize it exactly the same way that you thresholdize Bonnet-Franklin, which is exactly the same way that you thresholdize the BLS signature scheme, because we're using basically almost a BLS signature. So another thing that you might be wondering if you know anything about KZG is, where are the evaluation proofs? Like evaluation proofs tend to be not very efficient to compute. But it turns out that there's this nice algorithm by Feist and Kovacevic that allows you to take some digest and basically batch compute all the evaluation proofs blazing fast. Like you can compute all of these proofs in like almost linear time. So that's almost constant time per proof. And what that means is that decrypting the ciphertext, at least in an asymptotic sense, is also very fast. Okay, so that finishes the outline of the construction, and so now I'll spend the remaining time talking about mempool privacy. So what's the goal of mempool privacy? So let's imagine that we have some sort of proof of stake blockchain that looks something like this, something like what's on the slide right now. So let's imagine that we have a leader in every round that builds a block based on transactions it picks from the mempool, and then it proposes this block, and then all the validators vote on the block, and then once the voting is finished, once the block is committed and ordered, they execute the block. So the idea behind mempool privacy is simply to try to blind the leader to the contents of the transactions that it's ordering. And the purpose of this is essentially to avoid the possibility of front running. And how do we do this? Well, usually we do this just by encrypting the transactions in the mempool. So when a client, instead of submitting a transaction in plaintext, it'll submit a transaction ciphertext that is encrypted with respect to a public key whose secret key is shared among the validators. And then the leader will propose a block with ciphertext in it instead of plaintext transactions. And then after the block is essentially committed to and ordered, but before execution, all the nodes will work together to decrypt every ciphertext. So like I was saying before, if you use standard threshold decryption to solve a problem such as this one, it's very inefficient. There's a big blowup. And this is because, so the blowup is actually, it's proportional to n times t, where n is the number, like the block size, the number of encrypted pending transactions that go into a block, and where t is the threshold for the secret key. So it's essentially a quadratic blowup. So there are actually lots of previous works that try to address this problem, try to get more efficient solutions to this problem. But as far as I know, the first work that gave a solution without relying on sort of reduced security, some guarantees, or trusted hardware, or an off-chain committee that provides the decryptions to the validators. The first work that essentially avoids all of these shortcuts is this work by Chaudhary et al. Last year. And they were able to give essentially a scheme that achieves full security and has like a really fast online decryption phase. It's, the decryption phase is n log n plus t, which of course is much better than n times t. But the problem with this work is that, as far as I know, it's essentially a theoretical work, because the trade-off for this, very fast online decryption phase is an expensive offline sort of DKG-like protocol. And this DKG, you might, so what's wrong with the DKG? Nothing's wrong with the DKG, but they're expensive. And usually, like, DKGs are run at the beginning of an epoch, when the stake changes, because they're so expensive. But this DKG, unlike other DKGs, has to be run every single time, every single block, essentially. So because of this, I think, as far as I understand, this previous work is completely impractical. So in contrast to that, our work, we get the same online fast decryption complexity, but there are no asterisks. Like, we don't have any sort of expensive offline setup phase per batch. So I actually wanted to talk a little bit more about an observation that this previous work made. And this observation has to do with malleability of the encryption scheme. So let's imagine that we are implementing mempool privacy, and we have an encryption scheme that's malleable. So now let's imagine that I'm submitting a transaction to the leader, and I want the leader to order this transaction in the next block. So if the encryption scheme is malleable, then the leader can actually do the following. So it can refuse to order my transaction, and instead it can order a related transaction. Essentially, it can ball the transaction ciphertext and propose this, this related transaction whose plaintext is, it could be almost exactly the same as my plaintext. Maybe it just, mauled the signatures, the signature field, for instance. So now this transaction gets ordered and gets decrypted, and it also reveals info about my original transaction, but my original transaction was never actually included as part of the block. So this is pretty catastrophic in terms of mempool privacy, and so this is the observation that this previous work of Chaudhary et al. Made. They observed that essentially to get mempool privacy in a reasonable way, you need your encryption scheme to satisfy non-malleability, or in other words, to satisfy this strong CCA security. And one really cool thing about IBE is that you can actually take an IBE scheme and generically transform it into a CCA secure public key encryption scheme just using additionally a signature. There's like a very simple sort of transformation. And this is actually a class observed in this older classical work. And we also show that this sort of generic and simple transformation applies to our batched IBE definition as well. So I'll just finish this part of the talk by giving some concrete performance numbers. So these numbers are for our CCA secure variant of the scheme, and therefore specifically for the time it takes to decrypt a batch of various sizes. And I guess the bottom line is that we're, even not counting for this expensive setup, we're competitive with this previous work. We're actually slightly faster, and then, of course, with the setup, we're much, much faster. Okay, so I'll just conclude by stating our results again. We have this new primitive called batched IBE. We construct it, and we also construct CCA secure batch public key encryption, and we also give an implementation that's competitive with previous work. So I'll just finish by thanking Aline Tomescu and Andrei Tonkink for very many helpful discussions related to this project. And I had a lot of other things I didn't have any time for, and I'll refer you to the work if you're interested. Okay, thank you.
Thank you, Rex. May I have time for one quick question, please?
Thank you for the nice talk. Just a clarification, did we lose with this change the ability to do the usual decryption of IBE, or is it still there?
I think that depends what you mean by the usual decryption. What do you mean by that? You're talking about the syntactic change that I introduced?
Yes, the syntactic plus what happens with a change of BLS.
I see. No, I think, yeah, I think you're able to do the same thing. There are limitations. I think I'm running out of time, so I'm not sure we're going to have a very meaningful discussion, but if you're interested, I can talk to you more offline about this.
Awesome. All right, let's thank the speaker one more time. The next session is in 30 minutes. We have a break. It'll be a consensus session.
Welcome back, everybody, for the last session of the day. It's the second consensus session. And for start, we will invite Professor Angelos Kiayas, Chair in Cybersecurity and Privacy in University of Edinburgh, Director of Blockchain Technology Laboratory, and Chief Scientist in IOG, to give us a talk. Angelos, the stage is yours.
All right. So thank you very much. And talk is the evolving art of consensus, post-blockchain theory and practice of consensus protocols. So we will start by asking the question, what flavor of consensus is solved by blockchain? So consensus comes in many flavors, as you know. And the one we care about in this venue the most is state machine replication, or SMR, and specifically a variant of this called ledger consensus. So protocols for ledger consensus have servers maintain logs that serialize incoming transactions that are submitted by clients. And consistency and liveness are the two classical properties that all SMR protocols should satisfy. But we must also add to this too a third property that we can call it resource-based access, which is an intrinsically blockchain type of property. And that's essential because in the blockchain setting, parties are unauthenticated. Hence, access to write to the log becomes problematic. Who gets to write to the log and how often? The answer of the blockchain setting that gives to this question is to identify a resource and distribute access in some way that is reasonable based on who possesses that resource. Now observe that given this element, what becomes important is who possesses how much of the resource at what time. So this highlights that time now is an important component, and the ledger that we should be building should understand time. Ledger access based on resources can now be used to create a token monetary policy that mints coins that are protected by public keys. And given this, we can transition from resource-based access to token-based access, where tokens are also recognized as an alternative resource to write in the ledger. And quite importantly, these tokens can also be sold. And that's an important observation for how the blockchain setting reimagines the state machine replication problem as a service that is bootstrapped in a bottom-up fashion. So let me explain what I mean by this. The way it works is that interested parties engage with the protocol investing resources, whatever resource is the one that is recognized by the protocol. Through their actions, they get access to the ledger to mint coins, subject to the token monetary policy, which is determined algorithmically. Subsequently, they sell those coins to other users that wish to access the ledger directly, and in this way, they offset their costs. Overall, an economy around the SMR service emerges that has the power to make it sustainable as long as the system itself offers some utility to the participants. And the viability of this approach has been illustrated by the increasing popularity of systems like Bitcoin, of course, for over 15 years, but also Ethereum, Cardano, Solana, and many others. So now that we have established a flavor of consensus that is aimed to be solved by blockchain, let's ask what kind of solution does the blockchain give to that problem, and specifically the Bitcoin blockchain. And let's look at it through the lens of cryptography and distributed systems. Now, the interesting part is that there is a number of characteristics and features in the solution of the SMR problem that is given by Bitcoin that are quite unique. So for example, the protocol operates in an entirely unauthenticated setting with dynamic availability, which basically means that parties, the number of parties is fluctuating, parties come and go without announcement. The protocol has a public setup. It has optimal communication complexity and even has the ability to self-heal after spikes of adversarial activity or even network splits. Now, what is interesting about this model is that it was an unexplored territory for the consensus academic literature when the Bitcoin blockchain was introduced. So basically, nobody from the academic side of things or the research side of things in distributed systems and cryptography were looking at this model. Moreover, another interesting fact is that this model and all its features were not spelled out in the original works that introduced it. Instead, it took long time and effort to extract, decode, and be able to communicate this threat model. So looking at the success of Bitcoin and other systems, one may ask, why even bother to develop and understand the model it suggests? Isn't it enough that these systems work? And the point I want to make is that if we don't understand the model, it will be hard to answer the question whether the protocol, the solution itself, can be improved. And furthermore, it will be hard to learn from it. It will be hard to extract its features and possibly use them to do other things that are interesting. Now, case in point about improving the protocol, energy expenditure has been a famous topic and highly contested in the blockchain world. So Bitcoin is famously energy hungry, and the question is, can we do away with this feature? And if we do, what do we have to give up? So an answer to this question comes in the form of what we may call the proof-of-stake gambit. So proof-of-stake will sacrifice something, and first and foremost, importantly, will sacrifice setup transparency. So the setup of Bitcoin is just a random string, like what sometimes in cryptography is like is called the random string in the sky. But in a proof-of-stake system, we will need now a public key directory. So we need a set of public keys for the system to start. And the resource that we're going to associate with the protocol is the number of coins that are associated with the public keys. The potential benefits here, of course, is that we might be able to use a lot of protocol design techniques that were developed over decades of work in distributed systems protocol design. So it's easier to port these BFT techniques and retain energy efficiency. But of course, the question when doing this transition is, can we retain the characteristics of the Bitcoin permissionless model without proof of work? Now, in the blockchain space, there were a lot of very interesting early systems, such as Peercoin in 2012 and Next in 2013, that laid out key ideas on how we may be able to go about this. So specifically, these ideas were that parties now should engage on the basis of the number of coins they have, so that's their resource, and furthermore, that some type of cryptographic lotteries that essentially are based on the concept of a verifiable random function is the key primitive that we can use to let parties prove to each other that they're eligible to engage in the protocol. So these ideas were used in some way, but unfortunately, there were many challenges that came with these constructs. So for example, it was early observed that the adversary can rewind these winning opportunities, can run them many times, perform so-called costless simulation attacks, or somehow grind those lotteries to their favor. These were all attacks that you could not do in any straightforward way in the case of Bitcoin. So the question that was looming was, is the protocol still secure, or is there a new attack vector that has not been anticipated before, exactly because now the attack surface of the protocol was bigger? So this question alone has motivated a lot of research in the blockchain space. And specifically for myself, it led to the Ouroboros, a family of protocols that illustrates how to retain many of these Bitcoin characteristics combined with the minimal energy expenditure that you get from a proof of stake. So Ouroboros has been deployed in the Cardano blockchain. And just looking back, I would say that the most intellectually challenging part of the work was coming up with a framework to analyze the protocol, not the protocol itself, which in its own right was relatively simple. But the difficult part was develop the proof framework within which we can meaningfully analyze it. So the Bitcoin-like features that we managed to prove with this framework include dynamic availability, self-healing, privacy for maintainers, clock synchronization, and even went beyond what the Bitcoin blockchain can achieve, offering things like fast settlement and high throughput, which is upcoming work. Furthermore, the proof framework itself was found use going back to Bitcoin, and using the same proof framework, we were able to analyze the Bitcoin blockchain in a more refined way, coming up with results such as a tight analysis of its settlement properties. So with this and many other efforts, such as the Ethereum merge, overall in many respects, proof of stake has been shown to be a good replacement for proof of work. And it does so, of course, with this promise of minimal energy expenditure. However, undoubtedly, using cryptographic keys in the consensus protocol increases the attack surface. And this may have serious implications to security, which we have to consider. So let's talk about security. And importantly, let's talk about how theory can help us reason about it. The point here is that security is an elusive concept because it tries to speak about things that shouldn't be. So theory helps us ground it to concrete terms so we can more easily communicate it to each other and understand it. So just talking a little bit about cryptographic security. In cryptographic security, what we have as a typical statement is like the one you see here on the left. There's a set of some assumptions that I can denote by A, and these imply that the protocol is secure. The interpretation of this, in the context of a protocol like Bitcoin, is that any subset of executions that is induced by a particular strategy of an attacker, where in this set of executions you have a property of interest being violated, will be of negligible weight across all executions. So it is very unlikely that you will see it unfold when the protocol is actually executed. However, as we just said, this statement is conditional on some assumption. So this leaves open the question whether the assumptions are true. And while some assumptions we can try to get rid of, for example, the random oracle model, or some others, let's say, we do have the stomach to keep. For example, we're willing to accept that factoring is hard or discrete logarithms is hard, so digital signature, we can have digital signatures that are unforgeable. There are others that are unclear how to justify, and especially a kind of that assumption is honest majority type of assumptions. So such threshold assumptions are convenient and often necessary in cryptography and distributed systems. But they're not easy to validate in the real world. So one problem with such assumptions is that they're not falsifiable. So Moninar, over 20 years ago in Crypto 2003, put forward this concept of falsifiability for cryptographic assumptions. That in a nutshell says the following. An assumption we make is falsifiable if we can sample a challenge for it and put it in a public place. And then, if someone breaks it, they can demonstrate that effectively and categorically. So factoring, discrete logarithm are the type of assumptions that have this falsifiability property. But this is not possible to do for a threshold assumption. So what can we do about these assumptions like that? So here is an observation that can transition us from the world of cryptographic security to a world of that we can call economic security and reduce the number of assumptions we have to make. To see the transition, consider the contrapositive of a standard cryptographic argument. The point is that the contrapositive statement, we may be able to interpret it in economic terms. So what's the contrapositive? If some assumptions imply that the protocol is secure, it holds then that if the protocol is attacked, then some of the assumption fails. And this is where we might attempt an economic interpretation. Translated for Bitcoin specifically, we can observe that a subset of executions of non-negligible weight, where a relevant property is violated, can be proven to result in a significant expenditure in terms of hashing power by the adversary, again, under certain assumptions. But importantly, now, the set of assumptions that we need for this statement doesn't have the honest majority assumption, doesn't have the threshold assumption. So by reducing the assumptions needed for the statement of security, especially non-falsifiable ones, we can bring closer such a security argument to be more acceptable in the real world. There is a catch, however. The moment you start talking about the economics of running a protocol and the economics of attacks, it could be the case that no one may be running this protocol anymore. And this brings us the prospect of so-called Nash dynamics. So Nash dynamics treats the protocol that each node is running as its strategy. And given that the protocol then is continuously running, clients and nodes participating may be tweaking their strategies, rationally trying to improve their utility, making choices that are influenced by both endogenous and exogenous reasons. In this way, the parties may end up in an equilibrium that acts like a sink in these large graphs of possible strategies that you can think. But it may also be the case that the parties keep going in cycles. There is no equilibrium, and the parties are just moving in this graph of possible strategies following those Nash dynamics indefinitely. And now this issue has serious implications for our economic security argument. Now, in Bitcoin, due to economies of scale and the variance of rewards, the participants can pool their resources together. And at the extreme point of this, just a few pools emerge, or even just one in the worst case, and then our observation and implication that an attack subset of executions leads to a significant expenditure may not be true anymore. The thing is that depending on the pooling protocol now that is executed, it's conceivable that an attacker can just target the pool operators alone and then violating a certain protocol property of interest at a fraction of the cost. So the lesson here is that it will be pointless to reason about economic security without a firm understanding of the Nash dynamics of the protocol. So with this preamble, let's come to proof of stake. What can we say about economic security in this setting? So is it the case we can get a significant adversarial expenditure in the case of an attack? First, a common misconception is that techniques like slashing can reconstitute economic security in the same way as Bitcoin, or even better in some cases. I mean, this is not true. And the issue is that slashing penalties are themselves recorded on the ledger, and that's what makes them effective. Hence, some form of ledger security should still remain if we are to ensure that these penalties are enforced in the case of an attack. So, for example, there are many protocols that are completely prone to censorship when the adversary controls over 2/3 of the resources. So it follows that we cannot just obtain economic security here with only slashing without some type of threshold assumptions. So we cannot get rid of threshold assumptions in the same way, let's say, that we do in Bitcoin. So what can we get instead? So the argument I want to make is that we can still get something that I call attack artifacts. So these are particular events, such as key exposures, coins being transferred to the wrong hands, penalties recorded on the ledger, and other relevant events whose presence is there because the attack took place. As a result, an execution drawn from a sample of non-negligible weight that exhibits a property violation will have a number of those artifacts, perhaps different artifacts in different cases. But the point is that we can completely catalog those events in a comprehensive manner. So in order to achieve economic security, just to summarize, we need to develop and understand the mapping of those relevant attack artifacts into economic costs, and also understand the Nash dynamics of the protocol. At the same time, as much as possible, we should eliminate incentives for detrimental protocol deviations, such as pooling and centralization, and we should minimize the attack surface of the protocol that is presented by invocation of subcomponents that may be attacked individually. And such components can be the network, the key storage, the clocks, the setup of the protocol, and so on. So to give some examples of what we can do, let's first talk about pooling, and I'll give an example from some prior work that we've done exactly on that problem. So this was published some 7 years ago, and the point was to accept that in a proof-of-stake system, pooling will take place. So what we do is accept that fact and try to influence the pooling towards high participation and decentralization by facilitating pooling on-chain. The key idea is to allow nodes declare their details on-chain, for example, their operational costs, address their address, their information, their characteristics, as well as pledge some stake. And then with this, using the ledger as an advertising bulletin board, you can think, attract delegations from others that will form the node reputation. To increase inclusiveness and participation, we can allow this to be pretty low barrier. And then we can use these nodes as the nodes that are running the protocol. Now, given this setup, the node rewards can come in epochs and can be divided from two slices. One is proportional to the node reputation, which is the stake delegated, and the other is proportional to the node's pledge. Now, a key characteristic here of the mechanism is that we cap those slices to a specific barrier, which is controlled by a parameter k. So the barrier is like 1/k of the total rewards. So to get the rewards in the end, the slices are further adjusted for the performance of the node. So if the node is not performing, we don't give rewards. The operators are awarded the first the operational cost they declared, then a profit, then everything else is distributed proportionally to the delegated stake. So what we prove about this construction is that an equilibrium of k-pools will emerge. Declaring the true operational costs is a truthful act, and by adjusting the parameter gamma, we can control Sybil attacks. But what does that mean? When thinking about Sybil resilience, the relevant metric here is a Nakamoto coefficient. This metric asks how many entities have to be controlled in order to break the protocol. So we deployed this reward scheme in an agent-based simulation showing that by increasing the Sybil resilience parameter, we can drive the Nakamoto coefficient value up for various types of initial stake configuration that follow stake distributions that are either Pareto or are sampled based on synthetic distributions on actual cryptocurrency statistics. And this is the diagram that you see on the upper right of this picture. The darker cells represent higher values of Nakamoto coefficient. So in the simulations, in each simulation that you can see an example on the left, the agents initially open many pools, and this is shown in the y-axis, but due to the Sybil protection parameter, these pools are not as profitable as they could have been profitable if they were operating a smaller number of pools, so they are closed, and eventually the system converges to a small number of pools. So this should be contrasted to a Bitcoin-like linear reward sharing scheme, which follows the logic more resources in the pool, more rewards, and you can see this a simulation of which at the bottom of the slide, which converges to a single pool, even if it is forced to start from the highest possible decentralized state. So aside of all these more theoretical or simulation aspects, and perhaps more importantly, the scheme was deployed on Cardano consensus layer, leading to a decentralized stake pool operator distribution, as we were measured it. And in other words, I think what's important here is that you have a game that was designed, theoretically analyzed, and then played with real rewards by real people and resulting to a decentralized configuration. So let me now move to key exposures and other attack vectors that are of interest in the context of economic security. There are a few different ways that have been proposed in the literature that come all with their downsides, and some of them implemented as well. So here are some examples, how to deal with key exposures and increase their economic costs. So trusted execution environments, of course, they do work, assuming that you trust the hardware. Then we have verifiable delay functions, and as well as key evolving signatures. In both cases, these techniques can hinder costless simulation attacks with keys that have been acquired after they have been used. But as I mentioned already, this only solves one aspect of the problem. It's not enough to remove entirely threshold assumptions from our economic security. Similar thing happens with slashing and dilution. Slashing is basically applying penalties in case of protocol deviations that in a way reduces the absolute stake of the attacker, while dilution is the act of reducing the reward so the relative stake over time is being diminished. So in both cases, these actions make sense if these are recorded on chain. In case we still need some threshold assumptions for economic security. Finally, the concept of one-shot signatures for quantum-enhanced cryptographic primitives works beautifully well against key exposure because it's basically a primitive that only allows you to sign a message once because the signature key itself is in quantum superposition, so measuring it by design destroys it. But of course, it comes with the obvious downside that you have to do this quantum computation. So finding ways to increase economic costs of key exposures is and remains an active area of research. So let's look also at some other aspects, network clocks and setups. Peer-to-peer networking is another thorny topic in these protocols. The question is like, these systems, especially at the dynamic availability setting, they would like bounded delays in order to work. And in general, having short delays is something that everybody wants. And how do you do that with peer-to-peer networks in a Byzantine setting? And I have to say something from a design perspective, this classic approach where we just treat the network as a black box is not sufficient. A more effective approach that can be followed breaks the barrier between the two and just designs the communication subprotocol and the consensus protocol together. Set of assumptions refer to what is assumed by the nodes to know at the onset when they try to connect to the network. And ideally, we would like these values to be correctly computed and sampled, and doing so should be verifiable. We can imagine some form of secure multi-party computation to be useful here, but the task is further complicated by the fact that we can have nodes that come and go in this dynamic availability setting. And so we should be able to handle that from a multi-party computation perspective. Proof of work can also come back into the game here as a one-off cost that can help us set up the system, but then not used afterwards. Finally, shared clocks cannot be assumed to be available. It should be the case that participants have local clocks that may be drifting, and we should be able to have a protocol that helps them synchronize. So let me wrap up and look at the road ahead. First, economic security and decentralization. These are important questions that we have to understand better and design systems that can achieve them. For decentralization, you can refer to this earlier session in the program today, where there's a lot of things that, as a community, we have to do to measure it meaningfully. For economic security, an ultimate goal here would be that all non-falsifiable assumptions are translated to economic terms, so we essentially end up with security statements that are more plausible. The state machine replication as a service paradigm, I think it's very inspiring. It can be relevant for other IT systems. I can give an example of the NIM protocol, which is a VPN, an anonymous communication system, and that is bootstrapped in the same way as a blockchain. So I would be keen to see this logic applied to other cases as well. So for example, we can imagine a fully decentralized machine learning model that can act as a public resource and bootstrapped in the same way as a blockchain. In terms of sustainability and monetary policy, an important consideration is how these systems and their economies that are built in can sustain exogenous shocks. So a functionality like a central bank, but implemented on-chain comes to mind here. And that's another interesting direction to go to. And speaking of going to, many of these systems are currently running. So the concept of sound governance and decision-making is of critical importance. So if we are to make this long-term infrastructure for information technology, there should be a way to understand how critical the question of governance is. And we're still quite far from effective governance systems. Something to keep in mind also in this context that humans have to be involved. And if they are involved, it's good to have a constitution that encodes what they can and cannot do. So this is an area of digital constitutionalism, which is a great opportunity for cryptographers, developers, and legal and political scientists to work together. Finally, I want to mention cryptographic agility, a very important notion that has to be upgraded to this blockchain setting, to this decentralized setting. These systems, we basically fixing them and we're driving them at the same time. So understanding how to do cryptographic agility in this setting is critical. So that's my final slide. And the final point I want to make, as a takeaway, if there's one point to make. So, let's all admit that we have been this guy at some point. Certainly I have. But let's also agree that it's good not to be this guy. And let's continue learning how to properly define and communicate the fundamental problems of this science of blockchain systems. So I want to emphasize that the ability to formulate and articulate succinct problem statements is a cornerstone of what is scientific advancement. And it is that which enables us to understand each other's efforts, build upon them, and make feasible to work together. So something I think that you would agree is completely necessary if these blockchain systems are to truly succeed and fulfill their potential. And ultimately, what we hope that they will do is that renegotiate information technology into more democratic, inclusive, and fair terms for everyone. Thank you.
Thank you for the talk. Maybe we can take 1 or 2 questions if somebody has a question. And please, can you prepare for the next talk? Thank you. If not, I would like to ask Aggelos, how do you envision a synergy of proof of work and proof of stake blockchains in the future?
Well, it can be in many ways, but certainly one is already mentioned in the talk, that proof of stake systems by themselves, they do have pain points like the setup, where they draw their initial assumption, and proof of work can be the basis of that. And a simple example of this, for example, is you can take the Bitcoin blockchain, you can treat it as a public key directory, and then there are protocols that can be built on top of it that improve, let's say, various features of it while retaining basically the stakeholder distribution of the Bitcoin blockchain underneath. So in this way, you can imagine that the Bitcoin forms a setup for proof of stake protocols to unfold.
Thank you very much.
Thank you.
Sorry, for time efficiency, we will take the rest of your questions offline.
Thank you.
Okay, so our next speaker is Ondine Jean from Purdue University. Okay, the stage is yours. Thank you.
So sorry about that. So hi, everyone. My name is Jian Ting. I'm from Purdue University. So today I'm going to present our paper from running on DAG-based blockchain. And this is a joint work with Annika Kate. I think maybe first of all, let's begin with a quick refresher. So what is blockchain? So basically, briefly, blockchain is a state machine replication that consists of 2 major entities. Clients, sometimes we call it users who want to use the blockchain service. And replicas, sometimes we call it validators or miners who are responsible for maintaining the blockchain ledger. So a common use case of blockchain is that the clients construct transactions to interact with the on-chain states. For example, to invoke the smart contract to modify the on-chain state. The replicas corrected those transactions into his memory pools. The memory pool is some, for example, memory or storage that was used to temporarily hold on the transactions. Replicas periodically package the transactions from the memory pool into blocks. Run a consensus protocol to reach an agreement on the blocks of the transactions, and eventually executed the ordered transactions to update the on-chain state. So during this process, a very important point is consensus protocol, which determine what transactions can be executed and finalized on-chain in which order. So there are several classic consensus protocols, including proof of work, which was used by Bitcoin, proof of stake, and a family of Byzantine fault-tolerant atomic broadcast. or sometimes we call it BFT consensus for short. And there are a lot of blockchains nowadays, and in this presentation, we will focus on the DAG-based blockchains, which use a new consensus protocol and a new memory pools. A representative DAG-based blockchain is Sui, which has been deployed in production. At the same time, many other blockchain companies, such as Aptos and Supra blockchains, are developing their own DAG-based consensus protocols. So what are the differences between DAG-based blockchains and the others? In a DAG-based blockchain network, clients send their transactions to a designated replicas. Replicas can propose the blocks with their received transactions in parallel. And the replicas repeat this process round by round. In each round, whenever he proposes a new block, the new blocks has to reference to a column of blocks from the previous round. So replicas repeats this process, and as time goes on, you can imagine that those newly created blocks, as well as the connections, will form a graph. So each replica will use this graph as his mempool. Transactions on the mempool does not mean they can be executed and finalized on chain. And like the existing blockchain protocols, the replicas need to reach an agreement on the order of the transactions. And note that transactions in the same block have already been partially ordered based on their indexes when the block was created by the replica. So the only thing replicas need to do to reach a global order is to reach an agreement for the order of blocks. To achieve this, DAG-based blockchain predefines some leader blocks and using some rules to decide if the leader blocks can be committed or not. And here, a very important concept is that when a leader block can be ordered, all his connected blocks should be ordered as well. So here, DAG-based consensus use a block ordering route to order the leader blocks as well as his connected blocks. So we will return to this block ordering route shortly. Before that, let's revisit another common place concept from running, or sometimes people call it from running attacks. So from running is a class of order manipulation that enable the adversary to make his transaction orderly and execute it before the victim transactions, even though the attacking transactions was created later. Here is a simple example to show how the from running work. So in this figure, a victim created a transaction, broadcast the transaction to the blockchain network, and his transaction will be temporarily held in the mempool. And at the same time, there was an attacker observing the victim transaction, and he also created his attacker's transaction, also broadcast to the network. By performing some from running strategies, the attacker can make sure his transaction eventually ordered and executed before the victim transaction. So how can from running be performed? There are many factors can be used to decide how to launch the from running, but in this presentation, we will focus on the from running from the consensus side. So we find that from running are subjected to the specific ordering rules. For example, in Ethereum, transactions are ordered based on the maximum extractable values. So here is a simple examples. The client sends his transactions to the Ethereum network, and there are kind of builders package the client's transaction into a block. And the replicas pick the block that he can earn the maximal profits from it to commit it to the ledger. So to perform the from running in Ethereum or any similar blockchains, the malicious nodes only need to, for example, by setting higher transaction fees or given higher tips to the replicas. And most of previous work focused on such blockchain and such from running strategies. In this presentation, instead, we focus on DAG-based blockchain, which order transactions in a different way. So a naive attempt for the from running in DAG-based blockchain is to from run transaction within the same block. So here we define such from running as intra-block from running. So the high-level idea is that, remember, clients will send his transactions to one replica. So if the replica is malicious, then the malicious replicas can place his transaction before the victim transaction into his created blocks, and then broadcast to others, and eventually, the attacker can make sure his transaction ordered before the victim transaction. So the intra-block from running is very simple. However, we find that there are several limitations for this kind of from running. The first one is that the malicious replicas will have fewer opportunities to launch the intra-block from running. Specifically in DAG-based blockchain, to avoid the same transaction to be packaged into multiple blocks, clients usually send his transaction to one designated replicas. So if the malicious replicas is not designated to package its transaction, so there's no way to launch the intra-block from running. And the second limitation is that such intra-block from running are more accountable. Basically, you can imagine that if a client sends his transaction to a specific replicas and realize that his block was from run in the replicas block, then probably in the future the clients will not send his transactions to this untrustworthy replica. So does that mean DAG-based blockchains are more resistant to from running? Unfortunately, in this paper, we disclose some new from running vulnerabilities. So the high-level idea is to exploit the block ordering route in the DAG-based blockchains. So and then to launch the so-called interblock from running. So here is a simple example. Assuming the client sent his transactions to a replica, and there was another malicious replicas. After observing the victim transactions, he created, we call it attacker's block. And then he broadcast his block to the network. And by performing some strategies, which we will talk about shortly, the attacker can make sure his block will be eventually ordered before the block that consists of the victim transaction. And eventually, the attacker's transaction will be executed before the victim transaction. So here is a very concrete example to show how a specific block ordering route can be exploited. So many blockchain, especially the early stage blockchain, DAG-based blockchain, use a so-called DR-first ordering route. So basically, in these ordering routes, each replica will locally interpret a leader block as well as his causal history as a tree, where the leader block is the tree root. And after establishing such tree, the replicas will run a depth-first traversal algorithm. If you have learned any data structure or algorithm calls, you must know how the depth-first tree traversal algorithm work. And after this, the replicas will correct this block, and then he reorder these blocks based on the wrong number. So here's very simple example, very concrete example. to show a specific block ordering route. We find that such block ordering routes exposes several interblock from running vulnerabilities. So the first one is connection priorities. Basically, it says that if a block was connected by more descendants, which is connected by more blocks from the subsequent runs, then the block is more likely to be ordered first. And based on this observation, we propose a specific from running strategies called Fisher attack. The high-level idea is that the malicious replicas, whenever he created his blocks, he excludes the blocks from the so-called target replicas, which consist of some victim transactions. And by doing this, the replicas basically create a gap between his created blocks and the target victim block. And by doing this, we find that the attacker can increase the possibility of launching a successful interblock from running. So the second ordering priority we figure out in the DR1st ordering rule is called digest priority. Basically, it means that if a block has a higher block digest, then the block is more likely to be ordered first. So based on this ordering priority, we propose an attack called speculative attack. The idea is also very simple. So once the malicious replicas observe a victim transaction in a block, he labeled the replicas that create the victim block as the target blocks. And then what he can do is to create multiple blocks and choose the one with the largest block digest to broadcast to the network. And because of this digest priority, the malicious block is more likely to be ordered first. So it is worth emphasizing that there are a lot of interesting from running vulnerabilities, but here, because of the limited times, we only cover some of them. So if you are interested in this specific from running strategies, please refer to our paper. So we implement this attack on several open source DAG-based consensus protocol, including Task and Bullshark. The Bullshark was used to be deployed in the SWI. And we also implemented baseline where the attacker performed nothing to see how effective our proposed from running strategies be. We are doing extensive experiments, including some local machine experiments and AWS environments. So there are several interesting experiment results I want to share. First of all, we find that different from running interblock from running strategies are affected by different factors. For example, the Fisher attack we propose mostly benefit from the number of the attackers. It is not surprising because with more attackers in the DAG-based blockchain, the victim blocks is connected like fewer. So based on the connection priority, the victim block is more likely to be ordered later. And the second interesting finding we have is the speculative attack benefit from the number of workers mostly, where the worker, actually the worker is some process that help the replicas to create new blocks. So if there are more workers in the network, the replicas can create more blocks at the same time. So, yeah. And we also find that the network scales will impact the attack success rate. Specifically, we find that with more nodes in the systems, the attack success rate can increase a little bit. One hypothesis is that with more nodes in the system, the latency between the nodes increase as well. So as a result, the malicious replicas have more times to react to the victim transaction and launch the specific from running attack. So we also think about some mitigations. The first mitigation is to replace the original block ordering route with some so-called fear ordering route. For example, we can order the blocks in the DAC-based memory pool based on their timestamp, which will be relatively fair. However, there are some issues, but here we will not talk about the issues for this mitigation. And the second mitigation could be we can encrypt the transactions such that the malicious replicas has no idea if the transaction can be from run or not. Of course, encrypted transaction will introduce some extra computation complexity. And the third one is that we can use a not deterministic ordering route to replace the original deterministic ordering route, such that the malicious replicas has no pre-information to manipulate the order of blocks. However, the not deterministic ordering mitigation also have some limitations. For example, he might break some partially dependency between the blocks. Last but not least, you can reorder transactions after performing the block ordering route. For example, in the current SWI network, they reorder the transactions based on the transaction feeds after they perform, after a replica perform the block ordering route. However, such reordering strategies are suspected to the existing from running strategies. For example, the malicious replicas can participating in the fee auctions, by setting higher fees, they can make sure his transaction order first. And here are some takeaways. So first of all, we find that the from running can be explored interblockly, in the DAC-based blockchains. And this kind of from running are less accountable because actually the client has no idea if the replica he designated can from run his transaction or not. And secondly, apart from the DAC-based blockchains, nowadays there are many other high-performance blockchains which adopt a multi-proposal algorithms. Basically, in those blockchains, the replicas can propose blocks in parallel, and then they, as far as I know, they use a deterministic block ordering route to organize and order the blocks proposed by multiple proposal. So for those blockchains, a very interesting research direction in the future is we can see if those kind of blockchains, those kind of multiple proposal blockchains are vulnerable to the interblock from running. Of course, the specific from running strategies are subjected to the specific block ordering route. So, and again, I want to highlight, so the from running strategies are subjected to the specific ordering route. That's being said, if DAC-based blockchain adopt another block ordering route, probably previous from running strategies will become ineffective. But yeah. So last but not least, we think such from running might lead to some performance degradation. For example, in the previous slides, when we mentioned the phishing attack, the malicious replicas actually are motivated to exclude it. some specific blocks. So by doing this, of course, the malicious replicas can get some benefits from it, but from the system performance side, if you exclude many blocks, then the throughput of the system will be decreased a little bit. Okay, so because of the limited time, I will stop by here, and I'm happy to answer any questions.
Thank you, John-Tin. Can the next speaker prepare? And we will take questions meanwhile. Okay.
Hi, great talk. I was wondering, how do you learn about the target transaction as a front runner? Because, so if I understand, as a front runner, I have to publish my transaction in the same round as the target transaction, right? Mm-hmm. So I have to wait for the block with the target transaction to be published, and then I try to publish my block later, but in the same block, or?
So if I understand your question correctly, you are asking how the malicious nodes learn like the victim transaction, like how. I think this is a very high level idea. So we actually didn't focus on like how the malicious replicas learn the if a transaction is victim or not. But I think somehow maybe in practice, the following scenario could happen. Like when the malicious replica receive a block, and he definitely know the transaction in that block, right? So he probably maybe use some, some tools to calculate if any of the transactions are profitable. And after learning that, he create his malicious transaction in his newly created block and broadcast his block to the network.
Right, but I mean, so you have to wait because the both blocks have to be published in the same round,
yeah.
Right? So I have to wait.
It doesn't have to be the same round. It doesn't have to be the same round. It depends on the block ordering route. So if the block ordering route will order the transactions, order the blocks based on the round number, then probably it will has to be the same round. But actually, there are many other factors that can affect, for example, actually in DAG-based blockchain, so the ordering are divided into multiple instances. So for example, if a block, even two blocks have the same round number, if they are ordering in different consensus instances, then the order might be, different a little bit.
Okay, thank you.
Thank you again, John-Tin. So our next speaker is Colin Finkbeiner from University of Connecticut. And he will talk to us about selfish mining.
Okay, perfect. So hi, everyone. Thank you all for being here today. In this talk, I'm going to tell you about our work examining the landscape of selfish mining attacks. And this is a class of strategic mining behaviors that threaten the security of blockchain consensus protocols. And this is a joint work alongside Mohammad Inaj, Julia Guskind, and Gautam Ashokba. So first, I want to tell you about our real motivation beyond how we decided upon this work. We were looking at fee-driven blockchain systems that offer distributed services, and we were thinking what happened when block rewards disappeared, and rewards were purely based on transaction fees. And one of the first things we were thinking about was the impact of selfish mining and its effect on security under this regime. And this led us to start looking to the space to understand what strategies exist, what are the different model settings, and what are the various configurations of the network. So at this point, we were a bit lost. The space was large, and it was unclear how to relate many of the works together. However, it pointed to a new problem. It was clear that there was a need to better understand the space, both for us, but also for the community as a whole. And for the rest of this talk, I'm going to tell you about our systemization framework we developed to do so. But first, I want to give a brief background on selfish mining. So to understand selfish mining, let's go back over a decade ago to the early stages of Bitcoin. So at this time, there's a widely held belief that Bitcoin was incentive compatible as long as no single miner controlled the majority of the network. In other words, miners were expected to earn rewards proportional to the amount of work they put in. Put simply, more work, more rewards. But in 2014, this assumption was challenged with the introduction of so-called selfish mining. The core idea behind this is quite simple. A selfish miner changes how they participate in the protocol. Instead of following an honest behavior, they adapt an adversarial strategy. So in doing so, they choose to risk wasting some of their own work for the chance to undermine others in the network and boost a share of rewards beyond what their mining power alone would justify. And going a bit deeper in how this works, selfish mining relies on strategically withholding and revealing blocks in a manner to waste the work of other miners in the network. And selfish mining begins when a selfish miner finds a new block. And instead of publishing it, they instead withhold it, keeping it hidden on a private branch of the chain. And from here, they will continue to try to extend this lead, secretly continue to mine on top of this private branch. And this will continue until some event triggers it to reveal some number of its blocks. For example, this might be a change between the public and private chain when a new other miner publishes a block. Finally, when they do choose to reveal some of their blocks, a selfish miner will eventually cause a fork. The goal in doing so is to get its branch of the fork included, and in fact abandoning the other miner's branch and wasting their work. So I also just want to note here that although I'm showing the whole chain being revealed, in practice this depends on the strategy. And without going into further detail, I do also want to notice that in practice, selfish mining relies on changing the difficulty threshold. And so going a bit more, the selfish mining work by Eyal and Sarir in 2014 introduced the first strategy, classic selfish mining, similar to what I just discussed. And in here they found that in the worst case, a selfish miner needed just 33% of the mining power for a strategy to be profitable. And by this I mean earning more than honest mining. And this was under a simplified model that only assumed a single attacker with no propagation delay, and where miners' only revenue came from block rewards. So naturally, this led to a lot of follow-up works, exploring how different selfish mining strategies might further impact security, as well as how different model assumptions might change performance of such attacks. We find, however, that this landscape, it's quite challenging to understand many of these works and understand the effects on blockchain security. This is partially because many of the works focus on particular paradigms, fracturing results to be largely model-specific. And this fragmentation presents a pretty clear challenge. Not only is holistic knowledge of selfish mining attacks necessary to use these observations in other blockchain security modeling and analysis, but also to build effective defenses. So demystifying this fragmented landscape was a central motivation behind our work. So, and to the best of our knowledge, no work has focused comprehensively on the attack side itself. Our work closes this gap. So we present a multi-dimensional and granular systemization framework that organizes selfish mining strategies and models. And in our analysis, we highlight numerous insights into both the relationship between these selfish mining strategies and models, but also their impact on blockchain security as a whole. And in addition, we call to attention a number of gaps, but we actually don't just stop here. To complement our systemization study, we go on to examine one of these gaps head-on, specifically exploring how selfish mining under a specific model setting where miners' rewards come purely from transaction fees, the so-called transaction fee regime. And here we explore both existing strategies that have yet to be examined under it, as well as look at new strategy types. And for our scope, we focus on papers that examine selfish mining attacks, as prior systemizations have focused on the defense side of this landscape. And specifically, we focus our work on either those that propose new attack strategies or evaluate existing strategies under new model settings, all of which that target the Bitcoin network. And based on the scope, we find a total of 24 works dating back from the seminal selfish mining work up until works from last year. And the first thing we do here is develop a systemization framework. And by analyzing these works, we devised the following systemization framework, organizing selfish mining strategies across selfish mining attacks across 2 dimensions: selfish mining strategy formulation and model formulation. And to provide more granular insights, we introduced a number of subdimensions for both of these. For example, for strategy formulation, this covers the profitability notion of a strategy, as well as the various means that strategy actions are triggered by. And on the other hand, for model formulation, we find model factors can be classified into 4 subdimensions. This includes the number of selfish miners, the various means of miner incentives, the assumptions related to the mining behavior of other miners in the network, and lastly, the configuration of the network as a whole. So ultimately, we find the performance of a selfish mining attack is the profitability of a selfish mining strategy under a given model. And the network security threshold is the minimum mining power a selfish miner must control for a strategy to be profitable. So in our examination, we find a large number of different strategies, leading us first to classify them into families according to their different distinguishing features. I already discussed selfish mining, so next, as the name might suggest, the stubborn selfish mining family miners act stubbornly to selfishly mine for longer, and this could be considered a riskier variant of classic selfish mining. Another thing to note here is that the strategies within this family are additionally composable, meaning they can be combined with each other to offer more flexibility. The partially selfish family, has a selfish miner attempt to recruit rational but not yet selfish miners to help join in selfishly mining on a still private chain. And opposite of stubborn selfish mining, publish N is a more risk-averse family than classic selfish mining, limiting the possible lead a selfish miner's private chain can have before they must reveal some blocks. And next, as the name implies, this family views selfish mining as an optimization problem to determine what actions would maximize profitability. So moving on, the intermittent paradigm alternates between periods of selfish and honest mining according to time. And the bribery class, a selfish miner attempts to bribe rational miners to build on their branch of the public chain. So comparing this to partially selfish mining family that attempts to also attract rational miners, there it's on the private, still to build on a private chain, where here it's a public branch. And next, again, as the name implies, this family leverages deep reinforcement learning to dynamically choose what actions would maximize profitability. And here, this family tries to avoid detection, having a selfish miner mimic honest behavior under higher network latency while still carrying out selfish mining. And last, similar to intermittent selfish mining, the improved selfish mining family again alternates between periods of selfish and honest mining, but instead of being based on time, it's now based on block value. Mining honestly in high value blocks, whereas selfishly mining on low value blocks. So taking a closer look at our first dimension, strategy formulation, I want to touch on our first subdimension, which examines the various strategy objectives or their notions of profitability. So here, of the 24 works, we find that 14 formulate new strategies, and we find that the majority of these could be considered profit maximizing, focusing their objective on maximizing profitability and expectation. One of the interesting insights we find here is that within this class, these strategies might consider other constraints, such as detectability or certain risk profiles that may affect his overall profitability. So compared to the profit-maximizing strategies, which often take in the order of tens of weeks to become profitable, another class of strategies have focused on reducing this time, showing profitability in just 2 weeks. We call this class time to profit minimizing, as they focus their objective on minimizing the time to profitability. So moving on to our second subdimension, under strategy formulation, alongside the strategy objectives, we additionally can examine selfish mining strategies according to their update criteria. That is, what triggers the actions of these strategies? And for this, we find strategies can be grouped into 2 main groups, lead dependent and context aware. So lead dependent strategies, as the name implies, relies only on the lead between the public and private chain to trigger the actions of a strategy. On the other hand, some strategies might rely on additional context to trigger some of these actions. This is what we call context-aware strategies. And for example, this might be relying on block value or knowledge about the current difficulty adjustment period to trigger actions. And for these strategies, another insight we make is that this additional context fosters more flexible strategies, which can in fact be more profitable. And now I just want to move on to our second main dimension, model formulation. So here we identify 4 subdimensions that represent the various model factors. Perhaps the clearest of these is the miner's revenue source, how miners in the model are rewarded for their work. This is whether this is with block rewards, transaction fees, or both. And we find that almost all the works assume miners are only rewarded via block rewards, with only 2 works considering rewards from both, and just 1 from only transaction fees. And an important takeaway we find here is that among these few works that do consider transaction fees, selfish mining was found to be more profitable than in models that only assume block rewards. Our second subdimension here is the number of attackers. That is the number of selfish miners competing with each other in the model. And with multiple attackers in the model, a selfish miner loses some knowledge about the chain while additionally facing new competition. And in effect, this drastically changes the performance compared to the single attacker setting. And this has led to the development of new strategies like the publish end family that helps mitigate this increased risk from competition. So as selfish mining is inherently reliant on wasting the work of other miners in the network, behavior of these other miners is a crucial factor for its overall performance. For example, are other miners considered to be honest, following the protocol specified, or are they rational, adjusting their actions in a way that would benefit them? And based on these assumptions, what a selfish miner can do might change. For example, rational miners might be able to be persuaded to cooperate, where if not, if truly honest. And only a small number of works have explored these assumptions to date. Okay. So maybe a less obvious, but just as important of a factor is the configurations of the network. That is, what are the assumptions about how miners communicate with each other? And we find that most works studied a simplified model of Bitcoin's network, abstracting away propagation delay. Similar to what we see with transaction fees, the few works that do assume non-zero propagation delay show it can actually make selfish mining more profitable. So now, throughout the development of systemization framework and examining these 24 strategies, we identified a number of gaps in the space. Here I just want to highlight a few. So maybe the most notably, we find many unanswered questions surrounding transaction fees, both how they might enable new strategy types, but also how fees affect existing strategies that have only been studied in the block reward only setting. And for the multi-attacker setting, while a number of works have explored its impact on classic selfish mining, there's more work to be done exploring its effects on other strategies. And in addition, cases where multiple attackers might be running different strategies at the same time. And finally, the impact of how various mining behaviors might play into the performance of existing strategies, but also realizing in new strategies. So now I want to move on to our second thing, complementing our systemization framework in these found gaps. We actually go a step further and begin addressing one of these gaps head on. So specifically, we turn our focus to the biggest of these gaps, the transaction fee regime, and where miners are rewarded purely from transaction fees. And we go in to explore this across 2 main directions. So first, we want to understand the impact of transaction fees on existing strategies that have only been studied in the block reward only setting. And here we take a pretty extensive approach, examining them both under multiple numbers of attackers, as well as other mining behavior. And second, we explore how transaction fees, combined with these other assumptions, can enable entirely new strategy types. So a little bit about our implementation to do this. We conduct our experiments. To conduct our experiments, we extend an existing round-based mining simulator. And here we focus primarily on highlighting the effects of the transaction fee regime. And for the sake of time, I'll refer you to a paper full experiment breakdown. And our evaluations here are quite extensive. And for the interest of time, I'm only going to focus on one of them, the single attacker setting. Again, I refer you to a paper for a full breakdown of the other model factors. So first, in terms of extending existing results, our goal wasn't just to see how individual strategies performed in the setting, but to ask a bigger question. Is there a dominant strategy here, one that's the most profitable. And to explore this, we examined lead-dependent profit maximizing strategies. And to make sense of results, I first want to touch on a couple key parameters. So we denote a selfish miner's mining power as alpha. And in line with previous works, we denote the connectivity rate by gamma. And this represents the percentage of honest miners who receive the selfish miner's branch first during a fork. And as part of our evaluations, we also consider composable strategies, like those coming from the stubborn selfish mining family. And we denote a composable strategy with a circle symbol. For example, L circle F denotes stubborn lead selfish mining, composed of stubborn fork selfish mining. So with all this in mind, in this figure, we map out the full parameter space, examining the dominant strategy. And like the block reward setting, we find that honest mining remains dominant when a selfish miner has a low mining power. Whereas in orange, we see a region where a selfish mining strategy is dominant, specifically stubborn lead selfish mining, outperforming both honest mining and other selfish mining strategies. And finally, in teal, we see a region where a composable strategy, the stubborn lead trailing selfish mining, is now dominant. So from this, it's clear there's no single dominant strategy, and this aligns what's been previously found in the block reward only setting. What strategy is best depends where you are in the parameter space. With all this said, compared to the block reward only setting, we do observe some slight reductions to the security threshold. So for example, when gamma is equal to 0, stubborn trailing selfish mining threshold reduces from 33% to 31.5%, as found in the block reward only setting. So now I want to shift to our second direction. We find that the presence of non-honest miners alongside transaction fees can open the door for new strategies that can actively incentivize rational miners to favor the selfish miners chain. And our strategy to do this is inspired by the mechanics of a double spending attack. And more specifically, our attack is an incentivized variant of stubborn selfish trailing mining and remains fully composable with the other strategies in the stubborn selfish mining family. So our strategy combines trailing selfish mining with mechanics of double spending attack. And first, I just want to talk what trailing selfish mining is. Here, a selfish miner continues to extend their private chain, even when lagging behind the public chain, with the hope that they'll eventually catch up and be able to have their entire branch included. So here we utilize double spending to encourage rational miners to adopt a trailing selfish miner's branch. So to do so, a selfish miner posts a transaction, transaction 1, spending some currency from an account they own to another account they own. And they don't include it in their private chain, but others might on the public chain. So later on, if trailing and then eventually catching up, they can post a second transaction, spending the same currency to a third account they also own. And here the difference is they will additionally attach a high fee. So as this is double spending, only transaction 1 or transaction 2 will be valid. And here transaction 2 is only valid on the selfish miner's branch of the chain. And the fees attached here can incentivize rational miners to adopt this branch to be able to include transaction 2. So with all this in mind, I now just want to touch on a couple results. So here we examine the strategy under different incentives and in composition with other strategies, all in the presence of varying amounts of rational miners. And we find their incentivized strategy consistently outperforms the non-incentivized strategies, and in some cases this leads to significant improvements, with profitability thresholds dropping by as much as 7.5%. And here I just want to briefly mention that we find that these results additionally extend into the multi-attacker setting. We find that models where one or more selfish miners were running one of these incentive variants were found to be the most performant. And just to see a full breakdown of this and the other model factors, I again refer you to our paper. To wrap up, I just want to briefly highlight some future directions motivated by our findings as we discussed in our paper. So circling back to our original motivation in blockchain systems that offer distributed digital services, selfish miners typically play the role of servers, and so service fees make up a large part of their earnings. Miners' future revenue changes based on how newly published content from these service contracts and transactions. And in general, we find that this amplifies the effects of selfish mining, especially in the transaction fee regime. And this may foster new strategies further from what we discussed here. So hopefully this is something we can get back to after detouring into this deep dive of selfish mining, but it's a future direction furthermore. Next, we find that most research in selfish mining is modeled under Bitcoin. A number of works have studied selfish mining in other blockchains, including Ethereum and other proof-of-stake-based systems. Understanding how the impact of selfish mining changes under different consensus models is an interesting direction. And more so, there's a bigger question. Are there generic ways to examine selfish mining agnostic of these blockchain protocols? And finally, in terms of defenses, we find that there's various techniques, both for detection and prevention of selfish mining. However, many of these focus on classic selfish mining only under its original setting. Thus, it's crucial to develop more advanced defenses that account for this changing attack landscape under more realistic model settings. And that's all I have for today. Thank you. I'm happy to take any questions.
Thank you, Colin.
Yeah.
Anybody interested to pose questions?
This is probably a really dumb question, but has anyone looked at how people are using this in real life? Are people doing selfish mining, and what variants are they using?
Yeah, that's a really good question. So there's not been a lot of accounts of selfish mining actually found in practice. There's been a couple cases where on other blockchains there's behavior that's indicative of possibly selfish mining, but that's about it for this time.
Cool. Then thank you, Colin.
Yeah.
And let's move to the last talk for today. So we have waited all day long for this talk, so it must be good, right?
So thanks everyone for sticking around. Today I'll be talking about delay functions and dishonest majority randomness beacons. This is joint work with Joe Bonneau, Benedict Bunz, and Yuval Efron. So I'll be talking about the important problem of generating randomness in multi-party settings, and this problem is especially relevant in blockchains. And specifically, I'm considering a setting where you have many different parties, some of whom might be honest and some might be dishonest, and together they want to generate a random value R. And this kind of protocol is often called a randomness beacon or a coin flipping protocol, and I'll be using these two terms interchangeably. And you've probably seen that in blockchain settings, randomness is extremely important. Randomness is often used in consensus for leader or committee election, and randomness is often used because it gets us nice properties, like it helps mitigate adaptive attacks, where an attacker might attempt to predict who will become leader and engage in denial of service or bribery attacks. And randomness is also very useful for on-chain applications, such as lotteries, games, or DeFi. And here it's important that even a small amount of bias to this randomness can induce a huge expected gain. For example, if you had a slot machine on chain where an attacker could get a small gain in expected value, they could keep playing and amplify this gain. So we really want unbiased randomness. And there are many randomness beacons that are deployed in various projects, either used for consensus or for on-chain applications, or for both in some cases. And I want to highlight that Chia actually uses delay functions, which is the subject of this talk. But another thing I want to point out is that some of these randomness beacons can actually be manipulated. And it's been shown that the beacons used in Algorand and Ethereum for consensus can actually, in theory, be profitably biased. So it's possible for an attacker to not only manipulate this beacon, but to gain some expected reward in doing this manipulation. And these are theoretical attacks. They haven't been observed in practice, but it's important to note that these protocols are, in fact, biasable. So this begs the question of what we want in an ideal world. And really, ideally, I think what we want is a stronger notion of cryptographic security of these protocols. We want the randomness to be both unpredictable and unbiasable by any computationally bounded adversary that is attempting to influence the protocol. And we want a very special kind of cryptographic security. We want this to hold even in the presence of a dishonest majority. And now you're probably thinking that in consensus, we already need to assume an honest majority. So why would we want a dishonest majority randomness beacon? Well, there are several reasons why this assumption is okay for consensus, but less comfortable for randomness beacons. And one reason is that in consensus, attacks are often observable. So this lets us impose financial penalties on parties who deviate from the protocol. On the other hand, attacks against randomness beacons are often silent. In one kind of attack, colluding participants can predict the output without changing their behavior in the protocol at all. So this kind of attack is entirely unobservable. And some attacks where you actually bias the protocol simply look like the adversary got lucky. So, if they win on-chain poker an unusual number of times, for a while it just appears that they're getting very lucky. So it's hard to set a threshold and say that this is definitely becoming adversarial behavior. And finally, there are some biasing attacks that simply look like network failures. So you can bias some protocols by just dropping offline at a convenient point. And this is fairly indistinguishable from a party who is behaving honestly but just had a network outage. So for these reasons, we really want our randomness beacons to be unbiasable even in the presence of a dishonest majority. Okay, so this turns out to be a very hard goal to achieve. Basically, none of the deployed beacons that I showed you have dishonest majority security. So why is this difficult to achieve? Well, I'll walk through a couple of sort of toy examples of a protocol and help to build intuition for this. In these protocols, I'm going to consider only two parties, Alice, who is honest, and Bob, who is malicious, and together they want to generate a random bit. Bob is going to try to bias the protocol to output 1. So a natural first attempt at a protocol would be to have Alice send some random value, Bob send a random value as well, and obtain the output by hashing their values concatenated. The problem with this is that once Bob sees Alice's contribution, he can always choose his to ensure that the output will be 1. So he can just pre-compute what the output would be and select his value to induce an output of 1. Okay, so the problem here was that Bob chose his input based on Alice's. We could try to fix this by having both Alice and Bob commit to their inputs before revealing. So Alice instead sends a commitment to her value, and Bob must respond with a commitment to his before Alice opens hers. So here he can't choose his value based on Alice's, but there's a different problem, which is that once Alice reveals her value, Bob can compute what the output of the protocol would be, and if he sees that it would be 0, he can simply pretend to go offline and block this output. So by doing this, he can ensure that the output of the beacon is never 0. And it turns out that this problem is actually fundamental. There's no way to design cleverer protocols to overcome this. Cleve showed in '86 that any two-party coin-flipping protocol can be noticeably biased by a dishonest party. So there's always some attack that Bob can perform that induces a bias. And the attack that Cleve shows is very similar to the one that I just showed. Bob just strategically chooses when to stop sending messages. And this basically looks like Bob just went offline. So it's hard to tell the difference between this kind of attack and an honest network failure. Okay. But Cleve's result was in a body of theoretical literature that has been pretty separate from the body of work from the blockchain community. In this theoretical line of work, most of these protocols aim to minimize the inevitable bias that Cleve showed you have to have in this dishonest majority setting. On the other hand, many of these works from the blockchain community actually achieve negligible bias, even with a dishonest majority. So given what I just showed, this might seem impossible. Cleave shows that it's impossible to have negligible bias with a dishonest majority, yet these blockchain works achieve it. And they all have one trick in common that they use to circumvent Cleave's impossibility result. And this is a delay function. So to show why delay functions are useful, I'll show one of these protocols called Unicorn. And Unicorn can be thought of as improving upon the first bad protocol that we saw. So before, we had Alice and Bob each contribute random values, and the output of the protocol was simply a hash function applied to their concatenation. But remember that the problem here was that Bob could pre-compute what the output would be given any choice of his contribution and choose his contribution accordingly. So because Bob could compute this function that determines the output, he could bias the protocol. And the insight behind Unicorn is instead of just applying a hash function to get the output, you could obtain the output using a function that's very slow to evaluate. And this is a delay function. So you can think of a delay function as something that's polynomial time computable. Everyone can eventually compute the output, but it requires many sequential steps. And so what this gets us is that Alice and Bob can eventually compute the output of the protocol by evaluating this function, but it's too slow for Bob to evaluate before sending his contribution. So now the protocol imposes some specified duration where Alice and Bob can contribute. They must contribute during that time. And then the output is obtained by evaluating this delay function. So crucially, Bob has to choose his contribution before he's had enough time to evaluate the delay function. And so he can no longer perform this attack where he chooses his input to induce an output of his choice. And so Unicorn achieves a provably negligible bias with a dishonest majority. Yeah, and this delay function construction paradigm is really the only one we know for obtaining dishonest majority randomness beacons. But while delay functions are very powerful, as we just saw, it turns out that they're also pretty expensive to deploy in practice. And there are several big challenges that we face in deploying delay functions. The first is that they often add latency to the protocol because you have to evaluate this slow function. The second is that you need to develop specialized hardware so that the honest parties can compute the function about as quickly as the malicious parties can. If there's too big of a gap in how quickly the malicious parties can compute the delay function versus the honest parties, then it becomes less useful. Furthermore, as I mentioned in Unicorn, you set some duration when the parties are allowed to contribute their randomness. This duration needs to be calibrated to an actual delay parameter that's used for setting the number of sequential steps needed to evaluate the delay function. And choosing a parameter that corresponds to a concrete wall clock time is quite difficult. And finally, compared to other cryptographic primitives, there are actually few candidates known that we can construct delay functions from. And there's also a limited history of analysis of these candidates. So while there's been some very good work in analyzing these candidates, there's not as much history as other cryptographic primitives. Okay, and to give one example of where these deployment challenges have arisen is with Ethereum, which was looking into deploying a delay function called minroot. And so they developed some specialized hardware, but ultimately abandoned this plan of deploying minroot, in part because there was some new cryptanalysis that raised some questions about how much parallelism could be used to speed up the computation. And while this isn't a practical attack, it sort of goes to show that there's been relatively little history in cryptanalysis of delay functions. But while there are deployment challenges, it doesn't mean that deploying delay functions is impossible. Notably, they have been deployed in Chia, and so there's a real library that implements delay functions. There have been competitions in finding speedups and evaluating these delay functions. And so if you do the work, you can deploy delay functions, but it is quite expensive. So given these costs, one might ask whether we really need delay functions to build dishonest majority randomness beacons. right? Like we need something to circumvent cleave, but maybe we can make do with something that's simpler and easier to work with. And what we show in this work is that dishonest majority beacons and delay functions are actually equivalent. And the way that we show this is we start by assuming that you have a dishonest majority beacon, and we actually use this to construct an object that we call a weak delay function, which you'll see in more detail later. This is something far weaker than a VDF, or any other kind of delay function you probably think of. But then we show that you can in fact boost this weak delay function into a stronger, more like fully fledged delay function. And finally, we show that this notion of a delay function can then be compiled to build a dishonest majority beacon by essentially rebuilding the Unicorn protocol using it. So we have this nice equivalence between dishonest majority beacons and a formal definition of a delay function. Okay, so for the rest of this talk, I'll focus on this portion of our result, where we take a dishonest majority beacon and use it to build a weak delay function. And the way that I'll show this is by first supposing that we have a two-party coin flipping protocol, still between Alice and Bob as before, that Bob cannot bias. This means that Bob must not be able to run Cleave's attack. And so I'll argue that it means there exists some attack function that's hard for Bob to compute. This isn't a delay function yet, but then I'll show you how we can take this attack function and formalize it into an actual delay function. Okay, so first I'll start by opening up Cleave's impossibility a little bit. The idea behind Cleave's attack is Bob wants to ask in each round whether aborting now would cause Alice to output 1. If that's the case, then Bob can abort, Alice will output 1, and he's happy. So this is very similar to the attack that we saw before. But the problem here is that Bob can't actually perform this check. Alice's output could depend on her secret state, and so Bob actually doesn't know what Alice would output if he aborted. What Cleave observes is that Bob can instead ask a different question, which is, if Alice aborted now, what would I output? And now Bob can compute this because it depends only on his observations of the protocol so far and his internal randomness. And it's not immediate that this would be useful in telling what Alice would output if he aborted, but Cleave shows that in fact it is. So Cleave shows that there exists a round where if Bob performs this check and then aborts accordingly, he actually can introduce bias into the output of the protocol. Okay, so this is the main thing I want you to take away that we'll use to build the delay function. This is that there's a simple function that Bob can compute to decide whether or not to abort, and by doing so, he introduces bias. Okay, and remember we started with a protocol that can't be biased, so this must mean that Bob can't compute this function. Cleave's attack says that this function is polynomial time computable, so this must mean that Bob can compute this function, but it must be slow. It must be some kind of delay function. But we still need to formalize this. Okay, and so now this will be the most technical slide of the talk. I'll show you how we formalize this attack function into a weak delay function. But first I need to tell you what a weak delay function is, because it's a new notion that we defined that's slightly different from other definitions like VDFs. So a weak delay function has 3 algorithms. The first is a setup algorithm that generates public parameters. The second is a sample input algorithm that samples an input x on which evaluation should be slow. And finally, there's an evaluation function that takes an input and produces an output. Now, the properties that we want are very similar to, say, VDFs. First, we want efficiency, which is that the eval function is polynomial time computable. And we also want a very weak notion of sequentiality. So this says that it requires at least t sequential steps to compute eval with very high success probability. In contrast, VDFs say it takes many sequential steps to compute eval with non-negligible probability. So here I'm just saying it might in fact be easy to compute the function with 99% success. This would still be a weak delay function. We only need that the attacker can't compute the function perfectly. So this is like a very weak notion of unpredictability, which is why I won't show this, but it's a bit surprising that we can amplify this into a strong delay function. And just to contrast this with other kinds of delay functions, sort of full sequentiality would say that it requires t steps for even non-negligible success in predicting the output of the function. Okay. And the other differences between other delay functions that I'll mention is here we have no way to tune the delay parameter, and also there's no verifiability, so it's far from a VDF. Okay, so the way that we build a weak delay function out of Cleve's attack is we need to define these three algorithms, setup, sample input, and eval. And so remember I said that Cleve showed that there exists a round where Bob can execute this aborting strategy and introduce some bias, but it's not clear what round it is. So the setup algorithm simulates Cleve's attack on every possible round and finds a round on which it introduces bias. The public parameter is this round. The sample input algorithm simulates the protocol up to that round R, and then outputs Bob's random coins, the protocol transcript, and that round. So remember, sample input is supposed to output some input on which evaluating the function is hard. And now the eval function itself takes all of this as input and computes whether or not Bob should abort now. And this function must be weakly unpredictable because if Bob could reliably compute it, then he could bias the protocol. So we've succeeded in constructing a weak delay function. And now I'll mention here that it might seem immediate from Cleve's impossibility that you need some notion of slowness in order to get a dishonest majority beacon. But it's not clear whether that notion of slowness is like a slow sort of randomized task or a slow function. It's not clear until you formalize it that what you get out of it is any kind of useful delay function. So that is the main contribution of this formalization. We show exactly what kind of object this attack gives you. Okay. Yeah, and if you're interested in our amplification from this weak delay function to a full delay function, I encourage you to look at the paper. And there we also show how you can take our full delay function, which is also different from BDFs, and construct a unicorn-like protocol to get a dishonest majority randomness beacon. Okay, and now one question that I often get is whether we can use a different resource hard function instead of time. So unicorn kind of worked because it wasn't feasible for Bob to compute the output of the protocol before giving his contribution. And here we use the fact that the protocol was time-bounded, so we didn't have enough time to compute the output of the protocol. But you could imagine instead that maybe Bob is space-bounded during the protocol, and he doesn't have enough space to compute the output before giving his contribution. But the problem is that whatever resource we use needs to be limited during the protocol, so Bob can't do this biasing attack, but then it needs to become available after the protocol so everyone can actually obtain the output. And this is natural only for time, right? There's no natural way that you would be space-bounded during the protocol but magically get more space after. Whereas for time, you can have a limited duration protocol, but then everyone does get more time after if they're simply willing to wait long enough to have more time. The other problem with using other resources is in order to get security, the resource limit must be observable. So we could instead try to enforce that Bob is space-bounded, but Bob could have some secret computers that he's not telling us about, and we would never know. So an attacker can always lie about being space-bounded or some other resource-bounded, whereas for time, we can limit the duration of the protocol, which bounds everyone in time. So we don't need to have the same kind of trust assumption that Bob doesn't secretly have more resources than he claims to. Okay, so to wrap up, we've seen this result that delay functions and dishonest majority beacons are equivalent. And so what this says about sort of the landscape of randomness beacons is there's no way to build new clever protocols that avoid using delay functions, right? Like before, it might have appeared that we had these 3 paths. One path is to accept the deployment challenges with delay functions, do the work, and get dishonest majority beacons. A more hopeful path might be to design cleverer protocols that do tolerate a dishonest majority, but somehow don't run into the deployment challenges of delay functions. Or a third path might be to just accept honest majority security and then have more efficient protocols that way. But what we've showed is that this middle path is not really a path that we can take at all. And if you want to tolerate a dishonest majority, you really need delay functions. So we don't make a recommendation about which of these 2 remaining paths you take, but we help to characterize the landscape of what's possible. So now what's left is you really need to choose for your application whether you want dishonest majority security, in which case you need to cope with the deployment challenges of delay functions, or you can settle for honest majority security, which is also possible for some applications. Yeah, so here's a link to our paper, which appeared at Eurocrypt. I encourage you to check it out for more technical details, and I welcome any questions.
Thank you, Miranda, for the nice talk. Do we have questions?
Has anybody looked at getting randomness from the sun? Like every client takes a photo of the sun, counts the sunspots, because everybody can see it. Unless it's night, I guess, where you are.
Yeah, I'm not aware of anyone looking into this. I also don't see how it solves the problems with dishonest majority beacons. I guess the sun would give everyone a way to generate their randomness contributions to the protocol, but you still have this problem of combining everyone's contributions into a single random value that they all agree on. And in particular, you can't prevent these withholding attacks where, like, maybe you can even check that the value I contribute truly came from the sun, but if I don't like the outcome of the protocol that results from me contributing that value, I can always just decline to contribute it. So these biasing by aborting type attacks will still be present.
Do you have a question?
Yeah.
Sorry, go on.
So I'm not super familiar with the specific biasing attacks that exist already in the current implementations, but I wanted to know, like, if we really need a verifiable delay function that depends on a specific resource, or given that we're already in a context of a blockchain and we have validators and participating nodes, if we could use something like time lock encryption or something that's threshold based to force all the actors to only be able to continue once either the whatever is time lock encrypted or generated before the encryption is released, or once the validators come together to produce the threshold output or whatever it is.
Yeah, so for these threshold solutions, you need an honest majority. For time lock puzzles, I would suspect that any way you use time lock puzzles ends up getting you essentially a delay function. So the kind of delay function that we proved is necessary is much weaker than a VDF. So you're right, we don't necessarily need VDFs. Right. But you could imagine using time lock puzzles instead, and maybe the functionality you get in the end satisfies our notion of a delay function. Right. I guess we proved that must be the case.
Yeah, I guess my question was more like whether or not you need the I guess, well, you don't really need an honest majority, I think, for the, would you really need an honest majority for the threshold function? Because if you don't get enough people, I guess you could omit your part of the, I don't know, that's an interesting question. Because if you omit, you skip the whole round, right? It's not like you're not contributing to.
Yeah, maybe we can take this offline.
Yeah,
there are lots of different ways you can use threshold cryptography.
Yeah, thanks for the talk. I was confused about one thing. So you said Bob cannot efficiently compute whatever the probability of outputting one. Why does this give a delay function and not just a one-way function? So is there some...
Oh, yeah, because Cleve showed that this function is in fact polynomial time computable. And so it cannot, oh, I see, it could be a one-way function. But it must be hard in the forward direction, right? Like Bob can't compute this function within the duration of the protocol. So it must have some sort of fine-grained hardness. And we show in our model that it must be a delay function.
Because he gets extra information later that might make it easy to compute the function. Is that right? Because,
no. So in Cleve's attack, there is no more interaction after computing this function. So there is no more information that becomes available. This function is defined only on the protocol transcript so far and Bob's internal randomness. And so if you can't compute it during the duration of the protocol, it must be slow to compute.
Okay, fascinating. I have to look into paper. Thanks.
Okay.
So it seems that it was crucial basically that Bob, the way that Bob is doing the attack is basically by not providing a value, okay? Basically it's remaining silent. But that's basically going to hurt the liveness, okay, of your protocol. And you mentioned that that this kind of attacks could be silent, okay? So if I'm not providing any value, okay, I'm basically I'm hurting liveness. I mean, so it is invisible. I mean, it's not going to be the case. There will be some bias, okay, and no one will notice that because once I stop and I do not provide any values, okay, this is, you know, you're basically violating. So what am I missing?
Yeah, that's a good point. So I said that there are many silent attacks, but then I showed a specific attack that's not silent. So there are other silent attacks. The attack that I showed where Bob refuses to continue with the protocol is silent in a weaker, or not silent, but it's hard to detect in a weaker sense that you can't tell the difference between this attack and honest network failures. So here, if an honest party had a network outage, they would not be able to continue contributing to the protocol. But there are other attacks that, for example, predict the output of the protocol entirely silently. So there, nobody deviates from the protocol at all. So yeah, that's a good point. There exist these silent attacks. The particular one I showed is not the most silent of them.
Thank you again. That's a wrap for today. Enjoy your evening, everyone.